Mental Fatigue, Chapter 1 Introduction and Historical Survey. The facts of fatigue are conveniently divided into muscular fatigue, sensory fatigue, and mental fatigue. That the division is an artificial one does not need any explanation, for the individual is an organic whole, and a change in any part of the body is more or less accompanied by a change of the whole. Muscular and sensory activities are, as a rule, connected in various ways with the central nervous system. It is, moreover, very difficult to get mental activity which is entirely free from muscular and sensory accompaniments. Hence the division is made for convenience. When the terms mental activity and mental fatigue are used in this monograph, it does not mean that they are entirely independent of muscular and sensory activities or fatigue. We have generally used mental multiplication as a type of mental work, for the reason that its process contains hardly any sensory and muscular elements. Previous investigations of mental fatigue into the four classes based on its influence on organic processes, motor power and reaction time, sensibility of the skin, and the efficiency of mental functions. 1. The investigations of mental fatigue through its influence on organic processes. Investigations have hitherto been confined to three processes, namely pulse, temperature, and metabolism. 1. Changes in the pulse rate. So far as the knowledge of the writer goes, the first attempt to measure the relation between mental work and changes in the pulse rate was made by John Davy in the paper entitled On the Temperature of Man, published in 1845. Davy measured his pulse rate by the number of beats per minute on 18 nights soon after he completed strenuous mental work lasting for from 2 to 5 hours, and also on nights when no mental work was done. As a result of these experiments, he found that the average pulse rate at midnight after he had done mental work was 57 per minute, while it was 54.6 at midnight when none had been done. In 1881, Gley noted that the radial pulse rate is higher after such mental work as reading and working at geometry than after rest. Mosso concluded that the circulation was not the primary factor in psychological activity. In 1897, Feyscheid published the results of his thoroughgoing investigations on the subject. He measured the number of his radial pulse beats per minute on resting days and on days when he devoted 14 hours to strict mental work. He reported the results of 40 resting days and 72 working days in spring, and 4 resting days and 9 working days in summer. In the first series, the average number of beats per minute was 71.04 on the working days and 76.86 on the resting days. In the second series, the average number of beats was 69.8 on the working days and 74.44 on the resting days. Feyscheid gives the full data of the summer observations. By an investigation of these, the writer discovered that the average deviation was not so great as the difference between the two averages given above. Therefore, the difference cannot easily be attributed to mere chance. In 1896, McDougall found that there is an acceleration of the pulse in the first 10 minutes of the attentive state, which is followed by decline. In 1898, Binet and Henry noted that the pulse at the periphery is not necessarily changed by intellectual work, as change is not always accompanied by a change of the cerebral pulse. In the same year, Langmuir des Bancels reported measurements of his own pulse rate doing intellectual work lasting from 8 p.m. to 12 p.m. and doing periods of rest covering the same hours of the day. As a result of 4 days' experiments, he found that the pulse rate during rest fell rapidly to a certain point and remained practically without change for the remaining hours, and that during intellectual work it fell more gradually but lower than the lowest point in the rest period. The average pulse rates in the 4 successive hours in the work periods were 80.9, 72.2, 67.15, and 62.9. The corresponding figures for the resting period were 80.4, 69.8, 65.75, and 65.25. From 2 series of experiments lasting from 8 a.m. to 12:20 p.m., he obtained results in which the pulse rates in successive hours were 68.6, 64.5, 62.5, and 62.8 in the period of mental work, while they were 69.1, 63, 62.8, and 63 in the rest period. In 1909, Benedict and Carpenter reported the results of measurements of the changes in the radial pulse rate caused by mental work. During 4 hours of mental work, such as taking college examinations, the subjects were asked to count the number of radial pulse beats per minute. As a result of the experiments tried on 22 healthy young men, they found that the average number of the pulse beats per minute was 79 during the mental work, while it was 74 in the control experiment. They were not inclined to attribute the difference to the mental work itself, and said that it might be due to excitement on the part of the subjects, for it was the first time that they had gone into the respiration calorimetric chamber. To the writer, these averages seemed to be unreliable, for each subject measured his own pulse at any time that he wished during the examination. The result would be that if they measured their pulse oftener in the earlier hours of the mental work experiments than they did in the corresponding hours of the control experiments, the average pulse rate would be reported as relatively higher. For in both mental work and control experiments, the pulse rate decreased gradually. From the complete reports of these experiments, the writer found that 79 measurements were taken in the first half of the experimental period in a mental work experiment, while only 66 measurements were taken during the corresponding time in the control experiment. Since the average number of the pulse beats in the earlier half of the experimental period was 5.5 beats greater than that of the latter part, and the number of subjects tested was 22. The difference in the number of measurements in the first half of the experimental period alone would make the average of the mental work test 3.1 beats per minute greater than the pulse rate of that of the control test. To eliminate this source of error, the writer took the average of the pulse rate at the beginning and again at the end of the mental work experiment, and at the beginning and at the end of the control experiment. The average rates are 87.4 and 67.3 respectively for the mental work test, while for the control test they are 82.4 and 69.9. Thus, the decrease during the period of work is 11.1. During the period of rest, it is 12.5. In 1910, Billings and Shepard made a careful study of the change of heart rate with attention, performing their experiments upon 3 subjects. They measured the changes in the amplitude, the rate of respiration, and the pulse wave and rate in connection with the degree of attention, auditory, visual, and central. As a result of their experiments, the following conclusion is reached. With close visual attention, the breathing is uniformly decreased in amplitude. In rate, it is sometimes increased, sometimes decreased, and sometimes not changed at all. With auditory attention, it is nearly always decreased in rate, but changed irregularly in amplitude. The breathing in the kind of central attention that we used is very little changed. The changes are probably adaptive. They remove a source of disturbance. Deep breathing with its accompanying movements would interfere with looking. Rapid breathing interferes more with listening. With the effect of attention, the strain tends to increase the heart rate. Increased breathing, either in rate or amplitude, tends to increase the heart rate. Restricted breathing, either in rate or amplitude, tends to decrease the heart rate. For the latter reason, one often finds a decreased heart rate with sensory attention, particularly at first. With central attention, the heart rate is regularly increased. 2. Change of temperature. Claude Bernard reported development of heat in the nerves caused by mental work. Heidenheim, Helmholtz, and Rollenstein, according to Benedict and Carpenter, could not demonstrate that heat is generated in the nerves. In 1844, Davy reported the results of 18 series of experiments, several of them controlled tests. He found that the average temperature under his tongue at 12 p.m. was 98.4 Fahrenheit on the mental work days, while it was 97.4 Fahrenheit on the rest days. The most exhaustive study on the subject is perhaps that of Lombard, published in 1879. Performing his experiments on the same subject, he first investigated the influence of 4 kinds of mental work on the temperature of the 3 regions of the head, anterior, middle, and posterior. The result obtained was that the mental work of 4 kinds caused a rise in temperature in all 3 regions of the head, and that the degree of the rise and the rapidity of its appearance were different according to the kind of work and the region of the head. Lombard's further study of other individuals yielded similar results. In 1881, Speck reported that the average temperature on 3 resting days was 35.73 Celsius, and on 3 mental work days, 35.77 Celsius, the work lasting for from 2 to 3 hours. In 1884, Gley made 2 series of experiments on himself. In the first series, the temperature was taken every 5 minutes during mental work of from 1 to 3 hours, done between 5 p.m. and 8 p.m., and also during a rest at about the same period of the day. It was found that temperature fell not only during the mental work days, but during the rest also. This falls attributed by the observer to the immobile state which the subject was forced to maintain during the experiment. In the second series, a similar test was made while the subject was in bed, beginning about an hour after awakening in the morning, so as to free the subject from the influence due to muscular inactivity. In this test, unlike the results of the other, the temperature rose more than 1/2 a degree on the average during mental work of about an hour. Gley concluded from the result of these experiments that mental work raises the temperature. In 1898, Languier des Bancels noted that the fall of temperature under his tongue after 2 or 3 hours of mental work was 0.325 Celsius, while it was only 0.23 Celsius after a rest for the same length of time. In 1909, Benedict and Carpenter found that, as a result of the experiment tried on 22 individuals, the average temperature under the tongue was 98.9 Fahrenheit before and 98.4 Fahrenheit after about 4 hours of mental work, such as taking college examination. The average temperature under the tongue was 98.3 Fahrenheit before and 98.0 Fahrenheit after the same number of hours of rest. 3. Changes in metabolism. The problem of the influence of mental fatigue on metabolism has attracted the attention of such investigators as Hammond, Oppenheim, Speck, Mosler, Luciani, Sherman, Bocker, and Mayret. Their results, however, are of little value to us because they do not report carefully the amount and nature of the mental work done. Some of them compared the waste products of the human body during the day with those during the night, both as to quantity and quality. But the method is questionable inasmuch as they fail to take into consideration the fact that more physical work is done in the daytime as well as more mental work. The results which are important for us are quoted below. In 1881, Speck reported the results of experiments tried on himself and one other subject. Using a respiration apparatus, he concluded that mental activity has no influence on metabolism. In 1899, Atwater, Woods, and Benedict attempted to study this problem by the use of the respiration calorimeter. Their subject led a very quiet life for 3 days. During the next 3 days, he spent 8 hours per day studying a German treatise on physics and making mathematical computations. They found that during the 24 hours of each mental work day, the average nitrogen output was 13.1 grams and the carbon output 241 grams. The averages were 12.5 grams and 248.4 grams, respectively, for the rest days. In 1909, Benedict and Carpenter reported their careful investigations. They determined by the aid of a respiration calorimeter the amount of water vapor and carbon dioxide eliminated, oxygen absorbed, and heat produced by each subject during 4 hours of mental work and during 4 hours of rest. Their conclusions were: from the results of the data accumulated in this series of experiments on the effects of mental work on metabolism, it would appear that the pulse rate was slightly increased, the body temperature somewhat higher, the water vapor output increased by about 5%, the carbon dioxide production increased by about 2%, the oxygen consumption increased by about 6%, and the heat production increased by about 0.5% as a result of sustained mental effort, such as obtains during a college examination. Of these factors, those most accurately measured are undoubtedly the carbon dioxide eliminated and the heat production. On the whole, however, the increase of both of these factors accompanying the mental exertion is so small, and the exceptions are so numerous, that it would not be wise to say whether or not the mental activity exercised a positive influence on metabolic processes in general. Indeed, more than half of the subjects studied produced more heat in the control than in the mental work test, which might be considered as negative evidence. This is especially so when it is considered that altogether every precaution was taken to eliminate all other extraneous influences. It still remains a fact that, with many of these subjects, the experiments during the mental work period was their first experience inside of a complicated respiration chamber, and they were more or less disturbed by the novel experience, and perhaps more restless, that is, made more muscular movements than during the control period. In view of this fact, we are very strongly of the opinion that the results obtained in these experiments do not indicate that the mental effort has a positive influence on metabolic activity. 2. Investigations of the influence of mental work on motor power and reaction time. 1. Motor efficiency. Mosso was the first investigator who tried to correlate experimentally mental fatigue with motor efficiency. Using the ergograph, he found with himself, as well as others, that mental work resulted in a decrease of efficiency of muscular contraction. In 1896, Kempsey tested the motor power of school children with Mosso's ergograph at different times during the school day and reported a distinct correlation between the amount of mental work done and decrease of the ability to lift the weights. In 1900, Thorndike tested various individuals with Kettle's spring ergograph. The subjects made 100, 200, or 300 contractions at the rate of 1 contraction per second, with a rest of 1 minute after each 100 contractions. They underwent the test in the morning when no mental work had been done and on a day's class work, study, or office work. The comparison between the amount of physical force at these different times indicated that mental work affected no decided decrease in physical power. Thorndike closes his report thus: "To say that mental work does not necessarily decrease one's power to do physical work does not imply that the latter is independent of mental conditions, permanent or temporary, or that in individual cases whose mental makeup is well known, dynamic tests might not be indices of various mental conditions. Among these might be certain are the phenomena of fatigue. What is asserted is that the difference between a mind before and after it has worked for 6 or 8 hours cannot be detected by a record of physical work." Keller tested a schoolboy with the ergograph at different intervals during several days, giving him mental work between the tests. The difference in motor power indicated in the ergograph test is attributed to the mental work done. In 1903, Ellis and Shipe tested many persons for their reaction time and their ability to lift a certain weight before and after continuous mental work, and found no uniform change either in motor efficiency or in reaction time as a result of mental work. In 1906, Marsh wrote, "Where my own subjects noted mental depression or even headache on their records, the figures rarely fail to show a high grade of muscular performance at that time. But the younger the individual, the more prone he is to follow his feelings in the quantity and quality of his work." 2. Reaction time. In 1877, Bernstein found that the general fatigue from a day's work causes loss of speed of reaction. In 1896, Bettman found that 1 hour's mental work, such as adding single-paced numbers, caused a loss of speed of reaction, but also a decrease in the number of false reactions. The present writer has not found any difference between the reaction time in the morning before the day's mental work and in the afternoon after a considerable amount of mental work has been done. 3. Investigations of mental fatigue through its influence on the sensibility of the skin. The first attempt to measure mental fatigue by changes in the sensibility of the skin was made by Griesbach in 1894. He tested school children and adults with an esthesiometer at different times and obtained a decided decrease in the sensibility of the skin as the amount of mental work was increased. In 1898, Wagner and Vanold, following Griesbach's method, found that sensibility of the skin was weaker on the days of hard mental labor than on the days of rest. Binet and his collaborators obtained results corresponding to Griesbach's. In 1899, Luba published the results of his 2 series of experiments, one made at Heidelberg with 3 subjects and the other at Bryn Mawr College with 6 subjects. The method of investigation was that of Griesbach and Wagner. The threshold for 1 point was sought by a gradual decrease, and that for 2 by a gradual increase of the distance of the points of the instrument. The results of both of these series agreed in showing that mental work did not decrease the sensibility of the skin, and that the esthesiometric method was not a fit method to measure mental fatigue. German used the esthesiometer, with a distance of a little over 2 centimeters between the 2 points. He determined the sensibility of the skin by the number of right judgments. On 27 out of the 30 days covered by the investigation, a total of 42 tests was made. Of these 42 tests, 20 occurred in the morning previous to any study, while the remaining tests were made in the evening. The results of these tests showed that the errors were no more frequent in the evening tests than in those made in the morning. German concluded thus: in at least one normal case, the percentage of errors of cutaneous tactile discrimination bears no constant nor even relative correspondence to the mental fatigue experienced by the subject. In 1904, Bolton made a careful study with one subject. He followed closely the method used by Griesbach and measured the threshold of discrimination of 2 points before and after half an hour, and 2 hours of addition of one-place numbers, and found no difference in the discrimination before and after the mental work. Neither could he find a gradual decrease in the percent of right judgments according to the increase of the length of the mental work. 4. Investigations of mental fatigue through its influence on the efficiency of mental functions. For our present knowledge in regard to the problem, we are most indebted to Professor Kraepelin and his pupils, and their researches demand our special attention. In the present section, we shall first present a brief account of the previous investigations made outside of Kraepelin's school, and second, general outlines of the results obtained by Kraepelin and his pupils. 1. A brief account of the investigations made outside of Kraepelin's laboratory. One of the earliest attempts to study the subject was made by Galton. From the answers given by 116 teachers to the questions respecting the symptoms of fatigue of school children, Galton drew the following conclusions. First, mental fatigue causes worry and excitement. Second, fatigue occurs more often among those who work alone or are impelled to work hard through eagerness to excel. In 1879, Sikorsky made experiments on the influence of mental fatigue on voluntary movements like talking and writing. The results of his investigation showed that errors in these movements increased after certain mental work, and the amount of increase was in proportion to the amount of work done. The increase in the number of errors is attributed by him to a decrease in ability to distinguish small psychophysical differences, weakening of memory, and the appearance of mental excitement. The increase of the number of errors in the course of work was observed by Bergstein in 1891, Lasser in 1894, and Ebbinghaus in 1897. In 1895, Holmes tested school children in regard to changes in their ability to add as a result of continuous functioning, comparing the amount of work done and errors made in each of the 4 successive work periods, each period lasting for 9 minutes. This writer found that both errors and the amount of work increased from period to period. When gymnastics was introduced between the 2 periods, the errors were reduced to a considerable extent, while the amount of work done was unaffected. For this reason, the author regards the increase in the number of errors as a result of fatigue, the increase in the amount of work done as a result of practice. Examination into the nature of the errors revealed that the reproductive process, rather than the perceptual motor processes, is affected by fatigue. It also found that the children did no better work in the last period. In 1900, Thorndike published 2 articles reporting his 2 series of investigations. In the beginning of the first article, he gives a brief account of the 2 theories of mental fatigue. One of these, the mechanical theory, is that mental work causes a gradual decrease in mental efficiency in proportion to the amount of work done. The other, called the byproduct theory, is that mental fatigue is not a simple phenomenon. Just as muscle is fatigued because of the fatigue substances produced by its own activity, so mind produces as a result of its own activity various byproducts such as feelings of weariness, headache, and sleepiness. These products tend to weaken the ability to do mental work. The effect of fatigue, according to the theory, appears now and then suddenly in the course of work. The purpose of these experiments was to determine the relative merits of these 2 theories. 4 subjects underwent the tests in the morning after a night's rest, and in the evening after hard mental work. Tests were also made immediately before and after continuous exercise of special mental functions. The results showed that mental efficiency after mental work is not necessarily less than that before the work, and that in the course of 2 or 3 hours of mental work, the effect of fatigue is not strong enough to outweigh the effect of practice. His conclusions are as follows. 1. Mental energy, if it means anything, must mean as something which mental work uses up in regular proportion to the work done, but incompetence, mental fatigue, does not come in regular proportion to the work done. 2. According to introspection, there is no feeling of general mental incompetence. 3. The feeling of fatigue cannot be a measure of mental inability. On the whole, the results of the first series strongly favor the byproduct theory. The second series of experiment, recorded in his second article, was made on school children in order to determine the influence of schoolwork on their mental efficiency. The functions tested were written multiplication of 4 place numbers by 4 place numbers, marking misspelled words, drawing certain figures from memory, writing certain numbers, nonsense syllables and letters from memory, and also counting the number of dots on the chart, which was exposed 5 minutes. Every precaution was taken to guard against such errors as would come from testing a group of children specially selected, or with a different degree of practice, etc. The children met all the tests just as well after as before a day's schoolwork except one, i.e., memorizing nonsense syllables. In this experiment, the records in the late test were slightly inferior to those made in the early test. A fair claim to make on this basis of the results obtained, says Thorndike in conclusion, is that a regular day's work in the grammar school does not decrease the ability of the child to do mental work. The chief responsibility for mental exhaustion in scholars falls, I should be inclined to think, not on a creator who made our minds so that work hurt them, nor in the public opinion which demands that children shall do a given amount of work, but upon the unwise choice of material for study, the unwise direction of effort, the unwise inhibition of pleasurable activities, the unwise abuse of sense organs, and unattractiveness of teachers and teaching. The results of tests made on an adult subject, W, agree with the foregoing. In the first experiment, W marked every word containing both E and T on 151 pages of a book, each page containing about 725 words of text. He worked for 8 hours without rest. The number of words correctly marked was only a little less in the larger part than in the earlier part of the test. In the second experiment, in 3 hours of estimating the areas of small parallelograms of paper, the accuracy of W's judgment was constant with the first 2 hours, but fell off 7% in the last hour. In the third test, the results showed that fatigue, if present, did not outweigh the practice effect. In the fourth test, W measured the time it took him to correct examination papers for about 6 hours, and observed no sign of fatigue. In the fifth experiment, W tested the change in the time it took to go over 350 cards, on which were written titles of foreign books and articles, to decide in each case to insert it in a certain bibliography. Here too no fatigue effect was observable. The author asserts that the results do not at all disprove the existence of fatigue. On the contrary, mental incompetency is a fact. His conclusion is that the causes of fatigue are not mere decrease of energy, but highly complex byproducts of mental work. In 1903, Ellis and Shipe investigated fatigue in special mental functions resulting from general mental work. The mental functions tested were 1. Addition of numbers, 2. Writing of cubes of numbers up to 9, and 3. Memorizing nonsense syllables. 5 advanced students and a professor took part in the first experiment. The subjects worked on adding, cubing, and memorizing for 2 minutes, each at about 8:30 a.m. and at 5:30 p.m. after severe unremitting mental work, with rest only for luncheon only. The results were divergent with different individuals and on different days, but they utterly failed to show a difference in the amount of mental work done in the 2 tests. The same kind of tests made on the children between the ages of 11 and 16 yielded somewhat uniform results, testing to show that mental efficiency was much greater after the mental work. In 1903, Pillsbury studied the relation between the attention wave and mental fatigue. The efficiency of attention was measured by the ratio of the visibility to the invisibility of a grey ring on a slightly different background. The number of subjects was 5, including the experimenter himself. He found that the ratio was smallest after hard mental work, while it was greatest after rest. It was also found that the efficiency of attention corresponded to the total length of the wave, and it underwent diurnal periodicity, like the Traub-Herring waves of blood pressure. He gave the following explanation for the cause of the inefficiency of attention. We can explain our results if we consider the fluctuations of the attention a resultant of 2 physiological processes, and the degree of efficiency of the cortical cells, on the one hand, and the state of excitation of the vasomotor center on the other. The reinforcement of the medullary center would have its effect in decreasing and increasing the response of the cells, and would determine the ratio of fluctuation, but the proportion of the cycle in which they would be sufficiently effective to give rise to a sensation would depend primarily upon the freshness of the cells themselves. The degree of efficiency of the cells, then, would be measured directly by the ratio of the period of visibility to the period of invisibility of our minimal stimuli, while the length of the total wave would be a measure of the Traub-Herring wave. In 1910, Winch published his experimental study of mental fatigue in the evening schools. He took 3 classes which had homogeneous groups of students, and divided each homogeneous group into 2 equal groups, A and B, according to the results of the previous tests. The group A did the given fatigue tests at 8 p.m. and the group B at 9 p.m. The results of the tests made on those classes showed the work done by the group B was much worse than the group A. He concluded that evening school is of comparatively little profit, and that a short period of work after a day's labor is enough to produce low efficiency of mental functions. In 1911, Thorndike reported the results of an experiment made on 18 college students. The mental function tested was mental multiplication of 3 place numbers by 3 place numbers. The subjects worked for from 2 to 12 hours, each choosing a convenient time, and again for a short time next day. Efficiency was measured by the time taken to do each example. The amount of fatigue was measured by the difference between the time taken at the end of the continuous work period and that at the beginning of the test made next day. The average ratio between the average time per example at the end of the long work period and at the beginning of the brief test on the following day, expressed as a percentage, was about 61% for the group. He found that the number of errors varied inversely as the degree of efficiency, and that the feeling of fatigue bore little or no relation to mental efficiency. 2. The important investigations made by Kraepelin and his pupils. It was by Axel O'Hearn in 1889 that the first attempt to determine and analyze the work curves of certain mental functions was made. So far as the writer has been able to discover, he measured the efficiency 1. Of perception through ability to count letters, to search for given letters and to read proof. 2. Of mental ability to memorize nonsense syllables and lists of numbers. 3. Of association through ability to add one-place numbers. 4. Of motor functions through writing sentences from dictation and reading aloud. Each subject marketed his place on the stroke of a bell at the end of 5-minute periods, so that the amount of work in each such period might be computed. 10 professors and graduate students took part in the tests, which yielded the following results. 1. The predominant factors which determine the course of efficiency of mental work lasting for 1 hour are practice and fatigue. 2. This course of efficiency is represented by a curve, which rises at first and falls towards the end of the test, showing increase of efficiency followed by a falling off. The effect of practice and fatigue on efficiency are matters of common experience. Both are undoubtedly present through the tests. The length and the height of the rise vary in different individuals with different functions. 3. Individual curves are subject to other minor fluctuations. Many of them show a sudden rise in the first 10 or 20 minutes, observed by a sharp fall before they reach the point of maximum efficiency. This sudden rise is explained by O'Hearn as resulting from strain of attention. 4. The point of maximum efficiency, or the point where the fatigue effect begins to outweigh the effect of practice, comes sooner in the curve for the function which is more automatic than in that which is more purely mental. The average time at which the maximum point is reached is as follows. At the 24th minute in learning nonsense syllables, in the 26th minute in writing from dictation, at the 28th minute in addition, at the 38th minute in reading, at the 39th minute in counting letters one by one, at the 59th minute in counting letters 3 by 3, and at the 60th minute in learning numbers. 5. In measuring the effect of fatigue in practice, O'Hearn used the following formula. Practice equals m minus m to the power of 1 multiplied by 100 divided by m. Fatigue equals m minus m2 multiplied by 100 divided by m. Uppercase M stands for the point of maximum efficiency. M to the power of 1 stands for the first, and M2 stands for the second point of minimum efficiency. The average amount of practice thus obtained in each function is as follows: writing 1.8, reading 5.7, memory of nonsense syllables 6.2, counting letters 1 by 1 6.9, counting letters 3 by 3 11.1, memory of numbers 28.0. The average amount of fatigue is as follows: reading 5.9, counting letters 1 by 1 6.2, counting letters 3 by 3 6.9, writing 8.4, addition 15.4, memory of numbers 22.3, memory of nonsense syllables 38.5. The effects of both practice and fatigue in general are less in the less intellectual functions. The ability to memorize nonsense syllables is an apparent exception. Owen holds that the smaller net effect of practice is due to the far greater effect of fatigue. In 1892, Bettman studied in himself the influences of physical and mental work on certain psychological functions. To produce physical fatigue, he walked for 2 hours. For mental work, he added numbers for 1 hour. The influence on psychological functions was measured in the first series by 50 reactions, 30 minutes work in memorizing numbers, 30 minutes work in addition, and by 300 choice reactions in the second series only. In both series of experiments, a day on which the tests were taken after mental work was followed by a day of physical work, then by a normal day when the tests were taken after a period of rest, then by another day of mental work, and so on in rotation. The first series covered 12 days, the second 9. The mental work was done from 7 to 8 a.m., the walking from 6 to 8 a.m., and the testing from 8 to 9:10 a.m. in the first series. In the second series, the mental work was done from 7:30 to 8:30 a.m., the walking from 6:30 to 8:30 a.m., and the testing from 8:30 to 9:55 a.m. The results obtained were as follows. The reaction time was decidedly affected by the work of both kinds. In the second, actions in each experiment was, in thousandths of a second, as follows. A table is displayed on the page comparing normal day, mental work day, and physical work day, between 5 columns and an average. The percentage of false reactions was 1% on normal days, 2.9% on mental work days, and 26.9% on physical work days. The results of the choice reaction time test in the first series were about the same. The average reaction time was 389 sigma, with no false reactions on the mental work days, 309 with 3.6% false reactions on the normal days, and 340 sigma with 19.5% false reactions on the physical work days. The influence of both mental and physical fatigue increases the time of choice. The quick reaction time after the physical work is a result of excitement, which makes one react before the choice is made intellectually. This is indicated by the large number of false reactions. The tests of word reactions yielded the following results. The average word reaction time was 317 sigma on normal days, 391 sigma on mental work days, and 357 sigma on physical work days. Thus, continuous work on both mental and physical functions results in increasing the time of word reaction. The effect of practice is very great in memorizing lists of numbers. The excess in the amount of work done on the last normal day over that done on the first normal day was 38.5% of that done on the last normal day. On the last physical work day, it was 21.9%. On the last mental work day, 11.2%. These figures indicate that the fatigue resulting from both physical and mental work has an unfavorable effect on the influence of practice. The average number of digits remembered in the first and second halves of the 30-minute period was. A table is displayed on the page comparing mental, normal, and physical work days between the first and second half. In the addition test, the average number of digits done in the first and second halves of the 30-minute periods was as follows. A table is displayed on the page comparing mental, normal, and physical work day to the first and second halves. The 2 hours of walking and the 1 hour of adding then result in reducing efficiency, both in the function of memorizing and in that of adding. The conclusions which Betterman gives are, in substance, as follows. 1. Intellectual work of 1 hour and physical work of 2 hours have an unfavorable influence on the efficiency of mental functions. 2. Decrease in mental efficiency after work of either sort shows itself in the increased time taken for apprehension, choice, and association, in the weakening of memory, and in reducing the effect of practice. 3. Decrease in mental efficiency is as great after physical work as after intellectual work. Therefore, gymnastics, walking, and many other forms of physical exercise are not suitable recreation after mental work. 4. Motor inefficiency appears after mental work, and excitement of the motor centers after physical work. 5. Excitement in motor centers disappears sooner than mental inability. Its disappearance is hastened by taking up intellectual work. 6. The influence of fatigue, such as results from the test described above, disappears very soon, while that resulting from work such as research throughout the night lasts for many days. Amberg investigated the influence of periods of rest and work of various length on mental ability and its variation with different individuals. The mental functions tested were ability to add to one place numbers and to memorize lists of numbers. The addition research was of two kinds, a 1-hour test and a 2-hour test. The 1-hour test was made on the subject A1 with a 5-minute rest between two 30-minute work periods, 2 with 5 minutes work and 5 minutes rest coming one after another, and 3 with 50 minutes rest between two 30-minute work periods. The latter test was made also on the subject B. The 2-hour test was made on subject A and several others with a 15-minute rest between 2-hour work periods. The test of memory was made on two individuals, A and C, with a 15-minute rest between two 30-minute work periods. The influence of rest was studied by noting the difference in the amount of work done in the test with rest and that done in the controlled test, in which the subject worked without rest. 8 days were devoted to the experiment, with periods of work and rest of varying length, the controlled test coming on the first day, the rest test on the second day, and so forth on alternate days. Since the results of each rest test were affected by the practice gained in the controlled test of the preceding day, the following method was used to make the comparison possible. In the 1-hour test, half the average percentile gain in the amount of work done in each controlled test of that done in the preceding test 2 days before was taken as a coefficient of daily practice gain. A coefficient was likewise obtained in the 2-hour test. The influence of rest was measured by the difference between the amount of work done in each rest test and that done in the controlled test the day before, multiplied by 1 plus this coefficient. By dividing the sum of these differences by 4, the average influence of a certain length of rest was gained. The results thus obtained were 1. Different lengths of rest exercise, different influences on mental efficiency after rest. 2. Favorable lengths of rest are determined by the duration of work preceding it. For instance, a 15-minute rest was unfavorable after a half hour of work, but it was favorable after an hour of work. A 5-minute rest is better after a 15-minute work period than after a 5-minute work period. After 30 minutes of work, a 5-minute rest was better than a rest of longer duration. This is explained by the fact that during 5 minutes the effect of warming up is retained, while the effect of fatigue is largely offset. If the rest is longer, the effect of warming up is also lost. 3. Favorable lengths of rest are determined by the kind of work preceding it. For example, after a 30-minute work period, a 15-minute rest was reported favorably in the memory test, while it was unfavorable in the case of the addition test. Rivers and Kraepelin attempted to find the influence of different rest periods after the same length of work. The mental work used was addition of one-place numbers and only one subject was observed. There were 2 series of experiments. In the first series, there was a half-hour rest after each half-hour of work. In the second, there was an hour of rest between half-hour work periods. In both series of experiments, long and short days alternated, the long preceding. 8 days were devoted to the first series, 6 to the second. On the long days there were 4 work periods, on the short days but 1. The authors studied the 4 main factors which influence the efficiency of mental function: warming up, Anregung, spurts, Antrieb, practice, Übung, and fatigue, Ermüdung. The existence of warming up effect was indicated by its loss after the 1-hour rest. Comparing the amount of work done in the second half of each work period with that done in the first half of the following period, it was found that the gain was greater in the first series with a half-hour rest period, a phenomenon attributed to the fact that the rest period of a full hour in the second series caused a greater loss of warming up effect. This is even more significant since fatigue would be more completely offset by the longer rest period. In comparing the amount of work done on each successive 5 minutes, it was discovered that there was a sudden increase here and there in the amount done, which lasted but a few minutes. This is attributed to the influence of spurts, which are defined by the authors as follows. We designate these brief periods of greater accomplishment as spurts, in order to distinguish the special effect of the will from such ordinary influences as practice, fatigue, and warming up effect. The average amount of practice after resulting from 30 minutes of work, called, for convenience, the average daily practice gain, was determined as follows. The amount of work done in the first work period of each long day was subtracted from that done on the second short day, and the difference divided by 4, the number of the work periods on a long day, was assumed to represent the practice effect of a 30-minute work period of a long day. That of a short day was measured by the gross success in the amount of work done in the work period of the succeeding long day over that done on the short day. These results were averaged. The amount of fatigue in each 30-minute work period was determined as follows. To the amount of work done in a given period were added the daily practice gain, as computed above, and the daily practice loss, as previously determined. From this sum was subtracted the amount of work done in the period immediately succeeding it. The average amount of fatigue is given below, expressed as a part of the reckoned amount. A table is displayed on the page comparing the fatigue effect on the first, second, and third work periods compared to 30 minutes rest and 60 minutes rest. The fatigue effect in the third period is smaller after the 1 hour rest than after the 30-minute rest. The experiments conclude that the 30-minute rest was not long enough to eliminate all the fatigue effect which resulted from an equal length of work. The aim of the research by Weigand was to investigate the relative influence of the various changes of work on the recovery of efficiency lost through fatigue. The method used was as follows. The experimental days were of two kinds, namely change of work days and control days. During a test of an hour and 15 minutes, the subject did a certain kind of work during the first 30 minutes, changed it to another kind in the next 30 minutes, and resumed the first kind for the last 15 minutes. On the control day, the subject did the same kind of work as that during the first 30 minutes on the change of work day, for an hour and 15 minutes without change. The comparison was made between efficiency in the last 15 minutes on the change of work day and on the control day. In comparing the two, Weigand used the same method as that of Amberg to eliminate errors resulting from the order of the test. The tests were varied by using the different kinds of work in various combinations. 6 subjects took part. The results obtained were, in substance, as follows. 1. Change of work has a different influence according to the degree of difficulty of the work introduced for change. If the work introduced is more difficult, its influence is unfavorable, and vice versa. 2. Whether any given work is considered hard or easy depends on the individual and the degree of practice in the work assigned. 3. Fatigue in one function is transferable to another. 4. The insertion of a different kind of work has very often a favorable influence in the form of a spurt due to the change, Wechselcentrieb, which amounts to very little and disappears soon. 5. A favorable influence due to spurts comes very often in the state of fatigue. It depends on the motor excitement caused by change of work. Voss studied the minor fluctuations of a work curve in order to determine their causes. The author investigated the problem by finding, first, the time taken for adding each 2 succeeding figures, then the extent of deviation of each single addition time from the average, and finally the frequency of the occurrence of fluctuations of different lengths. Special apparatus was arranged so that a record of the time could be taken for each addition. The mental work employed was an hour of addition. The number of subjects was 3, including the experimenter himself. The results thus obtained were: 1. The time taken for a single addition ranged, as a rule, from 0.4 seconds to 1.2 seconds, but there were a few cases in which it took more than 1.2 seconds. A majority of the single addition times fell between 0.6 seconds and 0.8 seconds. 2. In all the subjects, the effect of practice increased the frequency of occurrence of a single addition time of 0.6 seconds and decreased the average deviation from it. It did not, however, increase the frequency of occurrence of the shortest addition time of 0.4 seconds. 3. The effect of fatigue, on the contrary, decreased the frequency of occurrence of an addition time of 0.6 seconds and increased that of 1.0 seconds. 4. The effect of the spurts tended to decrease the addition time to the minimum and made it very irregular. 5. The fluctuations were most frequent at lengths of from 2 seconds to 2 3/5 seconds. This duration, according to other researches made by the same author, was found to be about the same as that of fluctuations of attention. Therefore, he thinks that the fluctuation of the addition time is probably due also to the same change in the central nervous system. A very brief description of the investigation made by Lindley will be sufficient, as his methods are described in full in Chapter 5. The aim of the investigation was to find factors entering into the work curve, such as period of maximum rest, gain by practice, persistency of practice effect, susceptibility to fatigue, Urmud-Barkit, warming up effect, spurts, and individual variation. The subjects were 3 in number, including the experimenter. The mental function tested was the addition of 1 place numbers. Experimental days of 5 kinds followed each other in rotation for 26 days as follows. A day on which 1 hour's continuous work was done, 4 days in each of which there were 2 30-minute work periods separated respectively by the rest of 5, 15, 30, and 60 minutes. The 1 continuous hour work day again, and so forth. The following conclusions were reached from the series of experiments thus arranged. 1. The influence of rest is threefold: elimination of fatigue effect, loss of warming up effect, and loss of practice effect. 2. The best period of rest varies with individuals. With the 3 subjects tested, it lies between 15 minutes and 60 minutes or more. But, in case the warming up effect is great while fatigue is slight, work without rest amounts to fully as much as a work done after the period of maximum rest. The absolute excess and the percentile excess of work done in the work period before over that done after the different rest periods with the 3 individuals are given below. A table is displayed on the page comparing rest by 0, 5 minutes, 15 minutes, 30 minutes, and 60 minutes compared between the 3 subjects. 3. Capacity to gain by practice seems to go hand in hand with weaker persistency of practice effect and greater susceptibility to fatigue. 4. The greater part of the practice effect disappears within 24 hours after the cessation of work. Mysemer investigated the same problem as Bettman, namely the influence of physical and mental work on certain simple mental and motor functions, using for physical work 1 hour's walking, for mental work 1 hour's addition. Their influence on mental functions was measured by the ability to perceive 9 letters exposed for 0.017 seconds and to reproduce them after a half minute. A record is made of the number of letters perceived and reproduced, of those rightly perceived and reproduced, of those wrongly perceived and reproduced. Their influence on motor functions was measured by the ability to write numbers from 1 to 10 and from 10 to 1. 18 days were spent on the investigation in the case of mental functions, 21 days on the investigation in the case of motor functions. The physical work test, the control test, and the mental work test came in rotation on successive days in the order named. In the physical work test, mental and motor efficiencies were measured immediately after the walking. Before the control test, no work was done, and in the mental work test, measurements were made immediately after the hour of adding. The experiments yielded the following results. 1. The number of letters perceived and the number rightly perceived increased after both kinds of work, but more after the mental work. The number of letters wrongly perceived was greatest after the physical work. This was attributed to excitement of the motor centers by the physical work. 2. On the other hand, both walking and adding caused a decrease of efficiency in reproducing letters perceived after half a minute, and the decrease was greater after the adding. The number of letters reproduced wrongly also increased after work of both kinds, and this decrease in efficiency was again greater after the mental work. 3. Speed in writing and the size of the figures written increased after the physical work and decreased after the mental work. This corresponds with the result obtained by Betterman, in which the speed of reaction and the number of the false reactions increased after the physical work. This was explained by assuming that mental work exerts an inhibiting influence on the motor centers, while the physical work excites them. The aim of the investigation made by Heinlein and Kraepelin was to ascertain the effect of practice and fatigue. Long periods of work and rest have hitherto been used by such investigators as Amberg, Rivers, and Lindley. Heinlein and Kraepelin made a new departure by adopting short periods. An advantage of using shorter periods is, in their opinion, that not only can experiments be made on a greater number of individuals, but also a greater number of measurements can be obtained from the same individuals. A disadvantage is that the effect of work and rest is sometimes so slight that it is not measurable. The mental function used was the ability to add one-place numbers. On each experimental day, there were 4 5-minute work periods in groups of 2, separated by a 30-minute rest. On the first day, the 2 periods of the former group were separated by no pause, in the latter by a 20-minute pause intervened between the 2 periods. On the second day, the pauses were respectively 1 minute and 15 minutes. On the third day, 5 and 10 minutes. 3 subjects underwent the tests. The results of the experiments were: 1. Mental work lasting only for 5 minutes produced an appreciable amount of practice and fatigue. The ratio of these products determined efficiency. The amount differed with different individuals. For instance, W's practice gain was 9.6% and H's was 3.5% of his own average amount of work, while the K made progress only in the beginning and his average daily gain was very small. 2. The fact that the amount of work done on one day was greater than that done on the day before, in spite of the fact that efficiency at the end of one continuous work period was lower than at the beginning, indicates that the effect of practice outlasted that of fatigue. 3. The influence of rest was favorable or unfavorable. It eliminated, on the one hand, the effect of fatigue, so that the amount of work after rest was greater. Warming up effect was lost sooner than practice effect. The most favorable length of rest was that which resulted in the greatest ratio of favorable to unfavorable influence. The 5-minute rest was best after 5 minutes work in all the individuals tested. There lay an unfavorable length of rest between 5 minutes and a certain period longer than 5 minutes, differing with different individuals. For instance, with H the rests of 15 minutes and 20 minutes were unfavorable, while the 30-minute rest was again favorable. With W, the unfavorable length of rest lay between 5 minutes and 20 minutes. With K, the longer the rest, the better the effect. End of section 1. Chapter 2. Problems and experiments of the present investigation. To make the aim of the investigation clear, it is important that we should define the term mental fatigue. By mental fatigue, we mean the unfavorable and destructive effect which continuous mental work produces on mental functions. In a complete investigation, we should have to study, at least, its influence on the 4 large classes of mental and physical processes mentioned in Chapter 1. Lack of time for a more thoroughgoing examination of each problem, however, limits the scope of the present investigation to its influence on 1. Certain physical processes, 2. The feelings of fatigue, 3. Intellectual efficiency. We shall, in the following pages, state more specific phases of each problem and their relations to the results of the previous investigations. 1. In regard to the influence of mental fatigue on physiological processes, we recorded the pulse and the body temperature. In the matter of the influence of fatigue on the pulse, previous investigators are not agreed. Davy, Gley, and Billings and Shepard, for instance, found that mental work increased the pulse rate. Verschaid and Laguerre des Bancels have found that it decreased it. while Benedict and Carpenter found no change at all. These contradictory results may be due to the difference in the subjects used, or in the duration of mental work. We have no data on which to judge whether or not there was a difference between their subjects, but in regard to the different lengths of the work period, we do know that all of the investigators who reported an increase in the pulse rate employed a working period of less than 1 hour, while those who obtained opposite results had a working period of more than 4 hours. Consequently, if, as McDougall states, mental work increases the pulse rate at first but lowers it during the latter part of the work period, they're obtaining contradictory results. It's perfectly natural. If the shorter period of work is used, it is possibly only mental excitement that raises the pulse rate. These considerations lead us to direct our labors to the investigation of the following subjects. 1. The direction and amount of change in pulse rate during continuous mental work lasting long enough to produce enough fatigue to decrease intellectual efficiency. 2. The correlation between the change in the pulse rate and that in mental efficiency. In regard to the bodily temperature, all the investigators agree that mental work raises it. Here again a possible error may come in from the effect of incitement. Therefore, we have taken the same precautions as in the case of the pulse rate. 2. In regard to the relation of mental fatigue to the feeling of fatigue, Kraepelin, Thorndike, and some others agree that feelings of fatigue are not in any definite way related to the decrease of mental efficiency. We have investigated the problem by ascertaining 1. The direction and the amount of the change in the feeling of fatigue during continuous mental work. 2. The correlation between the state of this feeling and mental efficiency. 3. The correlations between the change in the feeling and the change in mental efficiency during continuous mental work. 3. The problem of the relation of mental fatigue to the change in mental efficiency is divided into 3 parts. 1. The first concerns the factors having influence on the efficiency of mental functions. The results of the previous investigations are not uniform. Kraepelin and his pupils, for instance, found that mental efficiency depends on practice, fatigue, warming up, Gilwonung, and spurts. But Thorndike found only the first 2 of these factors playing important parts. It is therefore necessary that a more careful investigation of the problem be made before we can know how far the change in mental efficiency is really due to fatigue itself. 2. The second concerns the effect of mental fatigue on the efficiency of the special mental functions exercised. Kraepelin, Amberg, and others discovered that the longer the work lasts, the longer it takes to eliminate the effect of fatigue resulting from the work. This they interpret as showing that decrease of mental efficiency is in proportion to the increase of the duration of mental work. But Thorndike and Ellis and Shope found that efficiency of mental functions was not less after certain hours of mental work. In the attempt to solve this problem, we have endeavored to determine a. The amount of fatigue caused by continuous work. b. The cause of the change in efficiency during continuous work. 3. The third concerns the transfer of fatigue. Kraepelin states that the greatest difference between mental fatigue and muscular fatigue is that mental fatigue has its effect on the whole field of mental activity, while muscular fatigue affects only the special muscles exercised. In short, Kraepelin holds that fatigue is transferred almost in toto. Thorndike, on the contrary, maintains the effect of mental work is very largely restricted to the special functions exercised. Our investigation of this problem was along the following lines. A. The influence of such mental work as that of a school day for a student upon the special mental functions, such as adding or memorizing. B. The influence of the exercise of the special mental functions on other functions. C. The correlations between the fatigue in one function and that in the other, both being affected by the same mental work. D. Individual differences. Experiment 1. The first experiment was made during February and March 1909 at Teachers College, Columbia University. The purpose of the experiment was to ascertain 1. The amount, rate, and the change of the rate of fatigue in the special mental function exercised, and 2. The amount of the fatigue transferred to certain other functions. The particular function tested was that exercised in mental multiplication of pairs and numbers like 2,645, 5,784, 8,324, 7,384, 7,954, 3,528, and 5,438 and 2,347. About 1,000 different combinations of figures were used. The order of the examples being made by chance. The distribution of difficult and easy examples is random. The subject of the experiment was the writer herself, but the danger that her presuppositions affected the results was precluded by the fact that the writer's knowledge of mental fatigue at that time was not enough to enable her to form any expectations of what form the fatigue curve in mental work would take. The experiment is divided into two parts by a slight difference of method, each part consisting of two series, the practice series and the fatigue series. Experiment 1, Part 1. Practice series. On February 2nd, the subject made the first test in the following manner. Using an ordinary watch, the subject set a time for starting. When the hand of the watch reached the point set, the subject looked at the first example and multiplied mentally, but with the original numbers in sight. The answer was written down as soon as it was obtained and the time recorded. Then the subject immediately took up the second example and repeated the same procedure. Thus she worked from 9:30 a.m. to 3:18 p.m. with a rest of 48 minutes for luncheon, and obtained the answers of 24 examples. From the recorded results of the first test, the subject found notable fluctuations in the time taken for doing an example, and that these fluctuations were not due to the fatigue produced by continuous exercise or the function, but were rather due to the lack of training for this work. This is probably correct, for as the subject became used to the experiment, the extraordinary irregularity in time disappeared and the curve became smoother. Also, the fluctuations appeared more in the first part of a period of continuous work in the first days of observation, while during the latter days the fluctuations became greater in the latter part of the continuous work, indicating that the former fluctuation was due to lack of practice and adaptiveness, while the latter was the result of continuous mental work. For this reason, it is important that when fluctuations resulting from fatigue are to be studied, the subject should be tested at or near the limit of practice and should be required to cooperate fully by always achieving his maximum. Therefore, before any attempt to determine changes in the rate of fatigue was made, the subject practiced on mental multiplication until the daily effect of practice became very slight. The amount of work done in the practice series is given in Table 1. Table 1 is displayed on the page. Time and errors in each successive mental multiplication of a 4-place number by a 4-place number, both numbers being presented to perception. February 2:15. Subject TA. Times are in minutes and seconds. Fatigue series. After the practice series described above, the subject made the experiment lasting from 1:45 and 40 seconds p.m. to 10:07:30 seconds p.m. with a stop for dinner, the results of which are given in Table 2. Table 2 is displayed on the page. Time and errors in each successive mental multiplication of a 4-place number by a 4-place number, both numbers being presented to perception. February 22. Subject TA. Times are in minutes and seconds. The introspection recorded after the experiment is as follows. I have no feeling of fatigue, but a little feeling of weariness caused by the monotonous work. My consciousness is clear and mood quiet. I was always guided by the hope of obtaining a true result. Pulse record. At the beginning of the experiment, 79. Immediately before the rest for dinner, 82. Immediately after the rest for dinner, 91. At the end of the experiment, 78. Experiment 1, Part 2. Practice series. From the experiment described above, it was discovered that the work was not difficult enough to produce sufficient fatigue. In order to make the task harder, a new condition was introduced. Instead of multiplying with the original figures in sight, the subject relied on memory for the figures and multiplied them mentally with closed eyes. The method was better than the earlier one, for it not only made the task more difficult, but it helped to eliminate sensory fatigue. When the subject forgot the original figures, she looked at them again, but as the time was made longer on this account, the loss of the original figures was counted against her. But this seldom occurred, as the subject was careful to commit the numbers to memory. With this new method, 6 practice experiments were performed. The results are given in Table 3. The introspections recorded by the subject after the experiment were February 24. The task is extraordinarily difficult. To multiply mentally with the new method is many times more difficult than it was by the other method. February 25. I do not feel well today. I studied hard all day before the experiment and have great difficulty in concentrating my mind on the figures. The work is very difficult. February 26. No feeling of fatigue after the hours of mental work. February 27. Lacking. February 28. The work was so interesting that I forgot meals. No feeling of fatigue. Fatigue series. Before going into the description of the experiments in this series, a word is needed in reference to the state of the subject's mind. By this time, the subject was accustomed to the concentration of attention upon the work and was little affected by fluctuations of feeling. She could do her utmost in each example. The writer is more and more impressed by the importance of this state of mind in the measurement of mental fatigue. To her mind, the results of the experiment made on one subject who can maintain an undisturbed mental effort yield truer fatigue curves than those obtained from carelessly conducted experiments made on hundreds of untrained subjects, for the errors in such experiments are not eliminated by the number of tests. The experimenter found it more advantageous to use an ordinary watch instead of the stopwatch, for this made it easier to record the time when a certain example was done. The slight error of observation is of no consequence in view of the long time required for a single example and the great variation of examples in difficulty. On March 3, 4, 5, and 6, the subject did the mental multiplication from 11 a.m. to 11 p.m. without any pauses except the 2 or 3 seconds between the examples for recorded time. But the subject had taken a heavier breakfast than usual at 10 a.m. and a light supper after 11 p.m. Her health was in good condition and she slept soundly at night. The contents of her consciousness during the experiments were very simple, all desires being completely subjected to the one desire to get true fatigue curves. The results of these experiments are summarized in Table 4. On the previous page, Table 3 is displayed. Time and error in each successive mental multiplication of a 4-place number by a 4-place number, both numbers being held in memory. February 24, March 2. Subject TA. Times in minutes and seconds. On the following pages, Table 4 is displayed. Time and errors in each successive mental multiplication of a 4-place number by a 4-place number, both numbers being held in memory. March 3 to 6. Subject TA. The times are in minutes and seconds. The introspective reports of the subject after each experiment were: March 3. In the morning I felt very well. I did not have any special feeling of fatigue in the course of the experiment. Towards the end of the test, however, it was hard to keep the original figures and partial products in mind, and I repeated the same products over and over again. Association became very slow and my mind wandered very much. March 4. I feel excellent after the work and am not fatigued at all. March 5. This morning I do not feel so enthusiastic about my experiments as I did yesterday. After work I have a little headache and feel very weak. March 7. After a week's concentrated mental work, I am as cheerful as usual. Physically and mentally no effect of the hard work seems to remain this morning. Along with the multiplication test, the test for transfer of fatigue was made. Before and after mental multiplication lasting for some time, the time taken for establishing connections between English words and their corresponding German words was measured. The procedure in the test was as follows. 2 sets of materials were prepared. One of them consisted of many lists, each containing 10 German words with their English equivalents. The other set consisted of lists containing the English words, which were in the first set, but arranged in different order. The subject first learned the German equivalents of the English words in the first set. When this was done, i.e., when the subject could call out the German words when the English words were presented, she took the corresponding list of the second set and wrote down as quickly as possible by the English words their corresponding German equivalents. The time spent in this process was measured by the instant of first sight of the list with the German and English words to the completion of the task of writing down the German equivalents. Before and after mental multiplication, 4 of these lists were learned and the time taken for learning each one recorded. The results of the experiments are given in Table 5. Table 5 is displayed on the following page. Time for learning German equivalents of English words before and after approximately 11 hours of continuous mental multiplication of 4-place numbers by 4-place numbers. Experiment 2. The purpose of this experiment was to investigate the influence of general mental work on the special mental and physical functions and the relation of one function to the other. For this purpose, the difference between the morning and the evening efficiencies, 1. In memorizing German equivalents of English words, 2. In doing mental multiplication, and 3. In pulse and feeling were measured. The direction and degree according to the varying duration of mental work were then worked out. The subject of the experiment was the writer herself. The experiment covered 78 days between February the 1st and the end of June. The method of testing the efficiency of memory is the same as that used in Experiment 1, except that 2 lists of German words instead of 4 were memorized. Efficiency in mental multiplication of a 3-place number by a 3-place number was measured, following the same method as in Experiment 1. States of feeling were classed as good, medium, or tired. Pulse rate was measured by the number of radial pulse beats per minute. In the morning at about 10 o'clock, before any mental work was done, and in the evening after a day's work, the subject measured her pulse and her efficiency in memory and in multiplication, using different lists and examples on each occasion. The state of feeling was recorded by introspection. With the records of these measurements, there were carefully written down the number of hours of sleep the night before and of mental work during the days when the tests were made. Health was recorded good when every physical function was normal, not well when it was below the normal, and bad when the subject was in any abnormal physiological condition. In this investigation, the subject performed the tests on all days when external circumstances made them possible. In order to avoid errors which possibly might come from suggestion or interest of some kind, the records of experiments which were obtained from day to day were kept out of sight. The subject carefully guarded against speculating on the results of the experiments. If there were errors at all in the results of the experiments, they were beyond the control of the experimenter. The results of Experiment 2 are given in Table 6. Table 6 is displayed on the following page. Efficiency in memorizing and in mental multiplication, pulse rate, degree of fatigue, and the state of physical well-being observed before and after each day of general mental work. Experiment 3. During November and December of 1910, the author translated into Japanese some chapters of Dewey's Influence of Darwin on Philosophy and other essays. The time taken for translating each page being recorded. Before and after a period of translation lasting for some time, the writer measured the temperature under the tongue. Since the materials of the test were not selected for the purpose of experiment and varied considerably in difficulty, one cannot expect to obtain accurate data on the change in the rate of fatigue, but it will be seen that the results are valuable when we come to discuss the relation of body temperature to mental work. The results are summarized in Table 7. Table 7 is displayed on the following page. Change of body temperature caused by mental labor as observed during the translation of English into Japanese, the speed of work being measured by the average time per line for each page. Experiment 4. The main series of experiments was performed during the academic year of 1910 and 11 at Teachers College, Columbia University. The primary purpose of the experiments were to investigate 1. The work curve of a single mental function exercised for 2 or 3 hours. 2. The influence of fatigue on one mental function or the efficiency of another mental function. 3. The relation of the amount of mental work done to the length of rest period. And 4. The relation between mental fatigue and certain physiological processes of the organism. The function tested for this continuous work was the exercise in multiplying mentally a 2-place number by a 2-place number. For the test of transferred fatigue, the mental functions tested were the ability to memorize nonsense syllables, the ability to add 8 columns of 10 one-place numbers, and the ability to call up the opposite of each word of a list of words. For the study of the relation of the amount of work done to the length of rest period, 3 different lengths of rest were used: 10 minutes, 60 minutes, and 180 minutes. To test the relation of mental fatigue to physiological processes, the pulse rate and temperature were measured before and after the mental work. Of the subjects of the experiments, all but 7 were professors and graduate students of psychology. Among the 7, the subject, CTT, was a student in the Department of Political Science and was taking graduate courses in psychology. The subject, SN, belonged to the Department of Philosophy and was taking undergraduate work in the Department of Psychology. The subjects, MM, GDS, and PER were a professor and graduate students in education. CTR and SW were the mechanicians of the psychological department. All except MM, GM, K, and PER were men. All but 4 acted as subjects twice or more than twice. These experiments can be divided into 2 kinds according to the different materials used for the measurement of the transferred fatigue. We shall call the first kind memory fatigue tests, in which the ability to memorize nonsense syllables was tested before and after continuous work in mental multiplication, and the second kind addition and association tests, in which the ability to add numbers and the ability to associate the words with their antonyms were tested. Again, the experiments can be divided into 3 kinds, according to the different lengths of rest period, namely 10-minute rest period tests, 60-minute rest period tests, and 180-minute rest period tests. The procedure of the tests was in the main as follows. In memory fatigue tests, the subject was required to sit quietly for about 10 minutes after his entrance to the experiment room. The experimenter measured the pulse rate of the subject by the number of the radial pulse beats per minute and tested the temperature under the tongue. The subject was then asked to memorize a list of 10 nonsense monosyllables. These syllables consisted of 2 consonants with a vowel between them, like gid, yat, and sut. At the end of 2 minutes, the signal was given and the subject wrote down the syllables remembered. Then another list of the 10 nonsense syllables was given to the subject to repeat the same process. The score was made by the number of letters remembered in their original order. For instance, if one remembered all 3 letters in one syllable, the score 1 was given. If he remembered only 2 letters in their right place, the score 0.7 was given, while for 1 letter remembered in its right place, the score 0.3 was given. When the memory test was completed, the subject was asked to be ready for the mental multiplication. With the signal go, the subject looked at the first example and memorized the 2 place numbers. With the eyes closed, he multiplied them mentally. As soon as the answer was obtained, it was written down. He immediately proceeded to the next example. The experimenter recorded the time when the subject finished writing each answer. The work on mental multiplication lasted for 2 hours, with most of the subjects, and 3 hours with a few subjects. After this period of continuous mental work, the memory fatigue test was given with different lists of nonsense syllables and by exactly the same method. The pulse rate was measured here. A definite period of rest followed this test. After the rest, the subject did mental multiplication again for 10 minutes. In the addition and association fatigue test, the whole process was the same as in the memory fatigue test, except the time spent in adding 8 columns of 10 single numbers and writing the answer under each column, and the time spent in associating antonyms with the given words were taken before and after the mental multiplication. A word must be added to explain the use of the rest period. In the 10-minute rest period, the subject remained in the experimental room and was allowed to do no mental work and spent the time in conversation with the experimenter. In the 60-minute rest period test, some subjects went to take luncheon and others spent it just as they did with the 10-minute rest. In the 180-minute rest period test, it was impossible to keep the subjects from doing something. The subjects who took this length of rest were a professor and an instructor who had to spend some part of the time for teaching. Compared with the intense and most concentrated mental work, like mental multiplication, however, the time they spent in customary classroom work was like a rest. The summary of the results of Experiment 4 is given in Table 8. On the following pages, Table 8 is displayed. Time spent per multiplication in each successive 10 minutes. Number of nonsense syllables held in memory correctly for 2 minutes. Time taken for adding 8 columns of 10 single numbers and writing down the answer under each column. And time spent in associating antonyms before and after the mental multiplication in each trial of each individual. CDT remembered all syllables in the second trial, so in the fourth trial, only 1.5 minutes were given instead of 2 minutes for memorizing 10 nonsense syllables, and yet the subject remembered all syllables as easily as before. For the second list, we shortened the time to 1 minute. Therefore, the number of syllables in the table is that which he memorized in only 2.5 minutes. Introspective reports of the subjects. After the experiments, each subject answered the following questions. 1. How did the subject feel after the long mental work? 2. What made the time taken for multiplying one example any longer than that for the other? Subject CDT. After trial 1, a slight pain across the eyebrows. The fluctuation of the time taken for multiplying one example is partially due to the difference of difficulty of different examples and partially to the disturbing thoughts. After trial 2, I have a slight pain across eyebrows. I feel fine generally. I wondered sometimes whether I was doing well and forgot the numbers. Sometimes I saw the table between my eyelashes and was disturbed. Once a voice outside made me stop a moment. After about 3/4 of the test was over, I found my hand was shaking. I have known it to do this only occasionally when playing chess. I had to stop it by thinking hard. After trial 3, I worked very hard today. The main difficulty is lack of ability to concentrate the attention. I was disturbed by what I saw whenever I opened my eyes. After trial 4, the process became almost automatic. Sometimes I could get the answer by the first sight of the example. Subject MS. After trial 1, I feel well in general, but have pain in my eyes, which I never had in reading and studying. I can visualize the numbers very easily. The process is very difficult, and the length of time is due to the inability to move. The mind seems perfectly blank. If I could only have moved across the room, I could have done the work much easier. After trial 2, I cannot say that I am tired. I have severe pain in my eyes and head. I got very angry when I could not do the work so well as I wanted. After trial 3, the sums of 9s and 8s confused me. I felt so discouraged that I felt most of my answers were merely guesses at those points. The smaller numbers seemed easy to me, and I felt no discomfort with the last sheet. I feel very uncomfortable. I have no headache. I could visualize very easily. I think much more easily than in the other test. Perhaps this is due to the prolonged test I have been taking on imagery since I took the last test. Subject RSW. After trial 1, I feel well. 2, some problems were done by shortcuts, e.g. 54 multiplied by 98 equals 54 times 100 minus 54 times 2 equals 5,400 minus 108 equals 5,292. Or again, 75 times 86 equals half of 8,600, or 4,300 plus half of this. Other problems were difficult to remember. That seemed the main difficulty. 1 or 2 distractions from noise outside. Aside from these, not much distraction. 3. Sometimes I felt clear-headed than at other times. I did not reduce the methods to automatic uniformity. It seemed to me that conscious effort entered mostly when I was obstructed. After trial 2, 1. Felt pretty good but yawned several times. Felt rather dull and confused most of the time. 2. Used no shortcut methods except near the start as noted. Hitherto I had always divided 4 instead of multiplied by 25 and multiplied 100 minus 2 instead of multiplied 98. But I decided it would be better to stick to a routine method. 3. The great trouble seemed to be the remembering of the given numbers, and I changed the method of retaining them. Hitherto I had repeated over 2473 when the problem was 24 multiplied by 73, and sometimes I had also said 27234743, this being the order of my multiplications. But this did not seem to work very well as a device for remembering the numbers, and I tried a new method which seemed to work better, i.e. taking the 4 digits around in a circle. Thus with the pair 3579, I begin with 3 and said 3597, 3597 2 or 3 times before beginning to multiply. Then I multiplied by 3, as in the usual way, viz. 3 multiplied by 9 equals 27, 3 multiplied by 7 equals 210, plus 27 equals 237. Next added to the partial sum 5 multiplied by 7, then multiplied by 10 and added 5 multiplied by 9. This seemed to be more reliable than previous methods of memorizing the numbers. 4. No visual images. I tapped the table, locating the digits as it were, but without getting there with any writing movements. Subject HAR. Conditions favoring rapidity. A. Inhibition of external stimuli. B. Inhibition of 1. Distracting or 2. Inhibiting ideas. 1. Irrelevant ideas. Not more than 17 in this case. 2. Especially unfavorable attitudes. Self-conscious fears of errors inhibiting from letting himself go. Positive side. An attitude of confidence or freedom. C. Shortcut method, e.g. multiplying by 97, multiply by 100 and subtract the product of 3 multiply the number. D. Apparently easier objective combinations. Subject JT. After trial 1, I feel pain behind the eyeball, dull and diffuse. The greatest length of time is due to the inability to keep the problem in mind and the partial products while arranging them for the addition. Subject MM. After trial 1, I have no pain in my eyes. The length of time is due to the number of repetitions that results. After trial 2, it was very hard for me to remember the figures. I had no headache. Subject PFG. After trial 2, I felt lazy when I was multiplying them. I had pain in my eyes and cramp in my right arm. Subject CTR. After trial 1, it became more and more easy to visualize the numbers. The trouble is that I do not seem to have enough energy to go on. Subject PER. After trial 1, I feel alright and have no pain in my eyes. Subject HLH. 1. Feel well and in average shape mentally. 2. Some problems are distinctly harder than others. The difference seems chiefly due to the difficulty of adding the two sums after multiplication has been performed. I can only imagine these two sums in their proper special position for adding for a brief moment. If the numbers to be added combine quickly enough, the addition can be made in this brief moment. If not, I have to start the adding all over again. I cannot hold the two numbers in the form of visual imagery. I have to keep saying either both of them or at least one of them, usually the multiplier, to myself. The multiplying comes quickly. Then I find that the original numbers are gone completely and I am left alone with the two products. I frequently find myself hanging on to these products, saying them over and over again, but being unable to get a special picture as to know which of the digits to add together. If I lose one of these products, I have to look at the paper again in order to learn what the original numbers were. 3. Was not conscious of a wave of attention, but the problems seemed to get easier toward the end of the series. In the first part of the series, I did not have a perfectly comfortable position, felt rather formal and restrained. As the test went on, I began to slouch down in my chair in a position which I frequently assume at my desk. Along with this change, the problems seemed to become easier. I cannot say whether I felt like assuming this attitude because the problems were not so difficult and permitted a little relaxation, or whether the change of position was what made the task easier. 4. In the beginning, I was conscious of nothing but the numbers, but as the test progressed, I found my mind wandering to other things, to accidental and irrelevant characteristics of the numbers, such as that the multiplier was just half or 1/3 of the multiplicand. During the latter part of the test, I once found myself in the midst of the problem, looking at a sparrow that had been playing on the window sill. Up to this time, I had ignored him. 5. In the beginning, it was easy to confine my attention to the problems, but towards the end it became more and more difficult to keep outside thought out of my mind, although there was, in spite of this tendency to distraction, the feeling that I was making better time in the test than the first part of the series. I found myself wondering if this increased speed was partially due to the fact that my mind wandered a little and enabled me to approach each problem without so much feeling of effort. End of section 2. Chapter 3. The influence of mental work on physiological processes. In Table 9, an attempt is made to find the difference in the pulse rate of subject TA in the morning and in the evening according to the different number of hours of mental work during the day. The days are divided into 10 different kinds according to the different number of hours of mental work, and under each kind there are given in pairs the morning and the evening pulse rates. In the table 01 means the days when the duration of mental work was from 0 to 59 minutes inclusive, 1 to 2 from 1 hour to an hour and 59 minutes inclusive, and so on. The data came from Table 6. Table 9 is displayed on the page, the relation between the degree of change in the pulse rate and number of hours of mental work. If we examine the average ratios of the different kinds of days on which observations were made, we find that the ratio does not decrease regularly with the number of hours of mental work, i.e. the pulse rate does not decrease in a strict arithmetical ratio to the amount of increase in the time of mental work. That the changes in the two factors in question are not wholly independent of each other is, however, shown by the following fact. If we take the average of the average percentages of decrease on the days of 0, 1, 1, 2, and 2, 3, that the percentages on the days of 3, 4, 4, 5, and 5, 6, and that of the percentages of the days 6, 7, 7, 8, 8, 9, and 9, 10, we get respectively 98.5 with AD of 6 and AD, T average to OBT average of 1.5, 96.1 with AD of 5.5 and AD, T average to obtaining average of 1.3 and 92.7 with AD of 1.3 and 92.7 with AD of 3.2 and AD, T average, obtain average of 6. This means, of course, on the whole, that by evening the pulse rate is decreased least compared with the morning rate when the subject has worked mentally less than 3 hours during the day, the ratio of the decrease being 1.5%, and that the decrease is greatest when the hours of mental work are from 6 to 10, the ratio of decrease being then 7.3% of the morning rate. The difference, however, might be greater if the pulse rates were measured independently before and after the mental work, for the following reason. Since the time of day at which the mental work was performed varies, the mental condition in the evening cannot be expected to be the same on all the days when the same number of hours were devoted to mental work. For instance, if the subject did 7 hours of mental work from 10 a.m. to 6 p.m. and spent the evening on rest or recreation, the mental condition at 10 o'clock in the evening, when the pulse rate was measured, might be only a little affected by the work of the day. This state of mind cannot be the same as that at 10 p.m. after 7 hours of mental work between 2 p.m. and 10 p.m. This tends to minimize the difference between the days of greater and less mental work. If therefore 5.8%, which is the difference between the average percentage when the mental work lasted for more than 6 hours and that of the days when it lasted less than 3 hours, means a real difference due to the greater amount of mental work. It would be still greater if the pulse had been measured just at the close of a certain amount of work. A fair inference from the actual figures given above would be that, so far as a particular subject tested goes, the average decrease of pulse rate tends to become greater as the duration of mental work increases. The chances are 8.9 to 1 that the true average percentile decrease of pulse rate during days of 0 to 3 hours of mental work will not exceed the average obtained for decrease of pulse rate during the days of 3 to 6 hours mental work, and the probability is 52 to 1 that the true average percentile decrease in pulse rate during the day of 4 to 6 hours of mental work will not exceed the decrease during a day of 7 to 10 hours of mental work. Let us now consider the correlations between change in pulse rate and in efficiency of certain mental functions. If the decrease of pulse rate can, to a certain extent, be a measure of mental fatigue, there ought to be some correlation between this and the decrease of efficiency in the mental functions tested, provided that the latter is a true measure of mental fatigue. Table 10 gives in full the relations of changes in the two factors. Using the formula R equals summary x multiplied by y divided by n multiplied by sigma 1 to sigma 2, we obtain a correlation of about minus 0.11 between the decrease of the pulse rate and the decrease of the time taken for memorizing the German equivalents of given English words, and a correlation of minus 0.11 between the decrease of the pulse rate and the decrease of the time taken for doing mental multiplication. If we use the median ratio method using the formula R equals half, open parenthesis, mid A divided by B ratio divided by variable A divided by variable B plus mid B divided by A ratio divided by variable B divided by variable A, close parenthesis. The former correlation becomes minus 0.243 and the latter minus 0.2193. Since measurements of the mental abilities were made by the times taken to do equal amounts, a greater decrease in mental ability is indicated by a larger percentage. A greater decrease of pulse rate is indicated by a smaller percentage. Therefore, a negative correlation indicates that the greater the decrease in the pulse rate, the greater the decrease in the mental efficiency of the function studied. A fair conclusion from the figures obtained would be that in the case of the individual TA, the decrease of the pulse rate is a little correlated with the decrease of inefficiency of the function of memory and of mental multiplication. Table 10 is displayed on the page. Rate of pulse for morning and evening rate of decrease, and the divergence of the individual percentages from the average percentage. Average time taken to memorize a German word in the morning and in the evening, rate of decrease, and the divergence of the individual percentages from the average percentage. Average time for mental multiplication in the morning and in the evening, rate of decrease, and the divergence of the individual percentages from the average. In the case of the group of individuals, the materials are obtained from the results of experiment 4, given in table 8. We find such differences of pulse rate before and after 2 hours of mental multiplication as are shown in table 11. Table 11 is displayed on the page, the pulse rate before and after 2 hours of mental multiplication, and the percentage which the latter is of the former for each individual, and for the average of the group. The figures in the table show that the pulse rate is invariably lower after mental work, the difference being 13.3% of the pulse rate before mental work. This difference, however, might be due to the fact that the subject sat for 2 hours with very little muscular movement, which invariably increases the pulse rate. Indeed, experiments tried on the subjects RSW and CHS showed that the pulse rate decreased during a 1-hour rest after 2 hours of mental work, and that the average rate of decrease is then about 5% of the rate immediately before rest. Consider now the correlations between change in the pulse rate and change in efficiency of certain mental functions, the facts being given in Table 12. Relating the divergence of an individual from the average change in the mental function to his divergence from the average gross change in pulse rate, we get a coefficient of correlation of about 0.4. 0.442 by the Pearson method and 0.366 by the median ratio method. Using the percentile change in pulse rate, we get a coefficient of correlation of 0.42, 0.429 by the Pearson and 0.413 by the median ratio method. The individual who loses most or gains least in the course of the work shows, to a considerable extent, the greatest drop, absolute or relative, in pulse rate. The similar relation of loss in ability to memorize nonsense syllables to a lowering of pulse rate is shown in full in Table 13. Relating the divergence of an individual from the average in one change to his divergence from the average in another, as before, we get a coefficient of correlation of about 0.795, 0.828 by the Pearson method and 0.75 by the median ratio method, using gross changes in both traits, and 0.76 by the Pearson method and 0.84 by the median ratio method, using the percentile changes. Table 12 is displayed on the page, the relation of change in pulse rate to change in efficiency in the process of multiplication from the first to the last 10 minutes of a 2-hour period. Table 13 is displayed on the page. The relation of decrease in the ability to perform the association test and the addition test, as described in Experiment 4, to decrease of pulse rate is shown in full in Table 14. Table 14 is displayed on the page, relating the divergence of an individual from the average change in the pulse rate to his divergence from the average change in the ability to associate opposites. We get a coefficient of a correlation of about 0.14, positive 0.32 by the Pearson method, and negative 0.04 by the median ratio method. Since the ability of the mental function is expressed by the time taken to do a certain amount of work, a higher percentage indicates a greater decrease of mental efficiency, while that means in the case of pulse rate a smaller degree of decrease. For this reason, a pulse correlation in the case described above means an inverse relation, i.e., an individual whose pulse rate decreased most during 2 hours of mental multiplication did best in the association test given after 2 hours of work. Relating the divergence of an individual from the average change in pulse rate to its divergence from the average and adding single numbers as before, we get a coefficient of correlation of about negative 0.134, negative 0.069 by the Pearson method, and negative 0.199 by the median ratio method. There is thus a correlation between the decrease of the pulse rate and that in the ability to add. On the whole, the facts from this small group of subjects favor the existence of a slight correlation between lowered pulse and lowered efficiency in intellectual work. Proof of its existence and a reasonably accurate measure of its amount can be had only by repeated tests with many more subjects. The influence of mental work on body temperature. Data obtained from experiment 3, given in table 5, give the results of many different observations with one individual on the difference of temperature before and after mental work. These are summarized in table 15. On the average, according to the figures in the table, the temperature rose only 0.1% during 2 hours and 3 minutes of translation work. Experiment 4 gives data on the changes of temperature in 6 individuals during 2 hours of mental multiplication, which are given in full in table 16. The average fall of temperature during 2 hours of mental multiplication is 0.2% in terms of the temperature before the mental multiplication. Table 15 is displayed on the page. The temperature immediately before and after certain hours of translation of English into Japanese in each different test. Consider now the relation between change in temperature and an efficiency of certain mental functions. According to the results of experiment 4, given in table 8, a coefficient of correlation of 0.22 is found to exist between the fall of temperature and the decrease of the ability to memorize nonsense syllables. The figure, however, is unreliable, for the number of cases is not sufficient. Table 16 is displayed on the page. End of section 3. Chapter 4. The influence of mental work on the feeling of fatigue. The writer has, by introspection, arrived at a conception of the nature of the feeling of fatigue very similar to that presented by Professor Thorndike, which runs as follows. When I try to analyze my feelings during states which in accord with the social consciousness I call feelings of mental fatigue, of inability to do mental work, I found in them emotions of repugnance at the thought of certain forms of mental activity, amounting sometimes to a sort of mental nausea, feelings of dullness or stupidity, by which names I mean a state of unsuggestiveness, of insipidity, cravings for certain familiar forms of mental relaxation, feelings of sleepiness, heavy feelings in the head, pains in the chest or back, from leaning against the table and sitting upright during work, and sometimes a feeling best characterized by the awkward phrase mental goneness, which reminds me of the feeling of physical faintness. This last is most likely the supposed feeling of incompetency, but I get it only very rarely and not necessarily after especially hard mental work. I fancy that it has some direct physical cause. I was constantly surprised to find myself, when feeling, as I would certainly have said, mentally tired, unable to demonstrate in the feeling anything more than emotional repugnance to the idea of doing mental work. On at least half of the occasions this seemed to be all there was. Comparing the introspective reports of the subjects on the feelings of fatigue with the actual efficiency of mental functions, Thorndike drew the following conclusions. Our third conclusion was that the feelings of fatigue, such as they were not measures of mental inability. Kraepelin has emphasized this fact, but chiefly in connection with the claim that we can be mentally fatigued without feeling so. What I wish to emphasize is that we can feel mentally fatigued without being so, that the feelings described above serve as a sign to us to stop working long before our actual ability to work has suffered any important decrease, which an experimenting psychologist could measure and use as a warning to us. In order to study the problem, the writer used two methods. One was to find whether the change of feeling is in any regular relation to that in the actual decrease of efficiency. We classify the feelings into three: good, medium, and tired, no finer distinction being practicable. The figures representing the degree of efficiency in mental and physical functions were grouped under the different kinds of feelings accompanying them. Comparing the averages of these three groups of figures, we can find the average conditions of mental and physical efficiency accompanying these different feelings. In the second method, comparison was made between the change in feeling and change in mental efficiency produced by mental work lasting for certain hours. In comparison, let 1 stand for the feeling good, 2 for the feeling medium, and 3 for the feeling tired. The change 1 to 1 signifies that the subject felt well both before and after certain hours of work. The change 2 to 2 signifies that the subject felt no better and no worse than usual before and after mental work. Thus 9 possible changes are represented by the combinations of these figures, namely 1 to 1, from good to good, 2 to 2, from medium to medium, 3 to 3, from tired to tired, 1 to 2, from good to medium, 2 to 3, from medium to tired, 1 to 3, from good to tired, 3 to 2, from tired to medium, 2 to 1, from medium to good, and 3 to 1, from tired to good. We express change in mental efficiency by the ratio which the time taken to do a given amount of work, or the amount of work done in a given length of time in a late test, bears to the time taken or the amount of work in a given length of time in an early test. The degree of change in pulse rate and temperature is indicated by the percentage which the number of beats or the degrees of temperature after is of that before the continuous work. We then group the percentages according to the different changes in feeling and accompany them and compare these groups. The third method is to obtain a coefficient of correlation between the degree of change in feeling and that in physical or mental efficiency. Since the classification of the feelings is so approximate, getting coefficients of correlation may not be a suitable method for the data. However, we shall use this method simply to supplement others. In getting the coefficient of correlation, we count the number of like and unlike sign pairs and calculate R by the formula R equals cosine pi percentage of unlike signed pairs. I shall report first results obtained from the facts of table 6 for subject TA. The degree of change in feeling from morning to evening is recorded by the method described above. The minus sign is used when the feeling in the evening is worse than in the morning, and the plus sign in the opposite case, e.g. the changes 1 to 2 and 1 to 3 are expressed respectively as -1 and -2. 2 to 1 and 3 to 1 are expressed as +1 and +2. We classify the differences into 4 groups according to the hours of mental work performed during the day and obtain the average difference of each group. On the days of from 0 to 2 hours of mental work, the average difference in feeling from morning to evening is 0. On days when the work lasted between 2 and 4 hours, it is -0.44. On days when it lasts between 4 and 6 hours, -0.58. On days of from 6 to 8 hours of mental work, -0.75. And on days from 8 to 10 hours of work, -0.87. The feeling of fatigue and the pulse rate. With the first method described above, we find that the average pulse rate accompanying the feeling good is 87.2 with AD 5.5 and AD TAV minus OBT AV 0.8, and the average pulse rate accompanying the feeling medium is also 87.2 with AD 6.5 and AD TAV minus OBT AV 0.9, and the average pulse rate accompanying the feeling tired is 85.2 with AD 5.4 and AD TAV minus OBT AV 1.1. The probability that the true average pulse rate accompanying the feelings good and medium will not drop lower than that accompanying the feeling tired is 6 to 1. With the second method, we find the following relations between the change in the feeling of fatigue and the percentage which the evening pulse rate is of the morning pulse rate. A table is displayed on the page. Change in pulse rate. If there were any relation between the change in the feeling of fatigue toward worse and the decrease of the pulse rate, it would be expected that the change in the feeling from good to tired would be accompanied by the greatest drop in the pulse rate, and that the percentage would be near 100 when the change in the feeling is 1 to 1, 2 to 2, or 3 to 3. The actual results are very different. The average percentage accompanying the change of the feeling 1 to 3 is 99.4, as next to the highest. The change 2 to 1 has a percentage of 90.8. On the whole, then, the pulse rate does not change in a regular relation with the change in the feeling of fatigue in the particular subject tested. With a third method, we find a coefficient of correlation of 0 existing between the change in the pulse rate and that in the feeling. The feeling of fatigue and efficiency in memorizing words. With the first method, we find that, in 41 measurements, the average time taken to memorize a German word is 15.7 seconds. With AD, 4.1 seconds, and AD, TAV minus OBT, AV, 0.64 seconds. When the subject felt good, 16.9 seconds. With AD, 3.5 seconds, and AD, TAV minus OBT, AV, 0.56 seconds. In 38 measurements when the subject felt medium, and 18.8 seconds, with AD 5.3 seconds and AD TAV minus OBT AV 1.18 seconds. In 21 measurements when the subject felt tired. Thus the efficiency of the function of memory is highest when the subject feels best and lowest when worst. With the second method, the following relations are found between the change in feeling and that in the speed of memory during the day. A table is displayed on the page, percentile change in time required to memorize. If there is any relation between the two, as in the results obtained by the first method, it is to be expected that the change of feeling 2 to 3 and 1 to 2 will accompany higher percentages, i.e. greater decrease of speed of memory than the changes 1 to 1 and 2 to 2, and the change of feeling 1 to 3 still higher percentages than the other two. The actual figures given above do not show much of this, yet there is indication that changes in the two are not entirely independent. Percentages accompanying 1 to 1 and 2 to 2 are about the same as those accompanying 1 to 2 and 1 to 3, but highest in the one accompanying 1 to 3. The single case of 3 to 1 is, however, also very high. With the third method, a coefficient of correlation of 0.13 is found between the change in one function and that in the other. The feeling of fatigue and efficiency in mental multiplication. By the first method, the average time taken to multiply mentally a three-place number by a three-place number is found to be 138.8 seconds, with AD 30.6 seconds, with AD TAV minus OBT AV 4.9 seconds. When the subject feels good, 142.9 seconds, with AD 20.6 seconds and AD TAV minus OBT AV 3.3 seconds. When medium and 151.3 seconds, with AD 28.8 seconds and AD TAV minus OBT AV 4.6 seconds when tired. The average number of wrong digits in each answer under these different conditions of feeling are respectively 1.0, 1.1, and 1.1. The chances are 7 to 3 that the true average time taken to do an example accompanying the feeling good will not be greater than that which accompanies the feeling medium. Chances are nearly 14 to 1 that the former will be smaller than that which accompanies the feeling tired. By the second method, we obtain the following relation between the change in feeling and that in the efficiency of the function exercised in mental multiplication. A table is displayed on the page, percentile change in time required for multiplication. According to the figures given above, we have a much smaller percentage accompanying the change in feeling 1 to 3 than that accompanying the change in feeling 1 to 1, 1 to 2, or 2 to 3. This is quite contrary to what we would expect if there were any regular relation between the two changes, that the percentages accompanying the changes in feeling 1 to 2 and 2 to 3 are greater than that accompanying the change of 2 to 2, and that the percentage accompanying the change in feeling of 2 to 1 is the next to the smallest, might however serve as an indication of some relation existing between the two changes studied. By the third method, we get a coefficient of correlation of 0.31 between a decrease of mental efficiency and a change for the worse in the feeling. The change in feeling is related during the duration of sleep the night before. By the third method, we find a coefficient of correlation of 0 between the change in the feeling toward the worse and the decrease of the number of hours of sleep the night before. In other words, the length of sleep the night before seems to have nothing to do with the evening feelings on the next day. Such results as this might not be obtained if the different durations of sleep ranged from 3 to 9 hours instead of from 6 to 9, as they did in our experiment. The results so far in this chapter concern the subject, TA. We next consider the relations of the feeling of fatigue to changes in physical and mental functions in the case of a group of individuals. Here we take the materials mainly from the results of experiment 4, given in table 8, and the introspective reports of the subject. In this experiment, the introspective reports were obtained only after the tests. Therefore, we are able to study only the relations of the efficiency in mental and physical traits to the feeling after continuous mental work. A change in any trait is expressed by the percentage which the efficiency after is of that before the work. The change in the feeling and that in the pulse rate. Of 9 individuals whose pulse rate was measured before and after the 2 hours of mental multiplication and whose feelings were recorded after the work, 5 reported that they felt medium. These had an average rate of late to early pulse rate of 87.5, with AD 8.3 and AD TAV minus OBT AV 3.7. The remaining 4 reported that they felt tired and had an average rate of late to early pulse rate of 79.6, with AD 3.6 and AD TAV minus OBT AV 1.8. On the whole, those who felt worse after the work were those whose pulse rate decreased most. The chances are 19 to 1 that the true average decrease in the pulse rate accompanying the feeling medium would be less than that accompanying the feeling tired. By the third method, we find a coefficient of correlation of 0.77 between the change in the feeling and the decrease in pulse rate. The changes in feeling and the efficiency of memorizing nonsense syllables. Of the 9 individuals, 5 reported that they felt medium. For these, the average ratio, which the average number of nonsense syllables remembered after is to that before the 2 hours of mental multiplication, is 101.2, with AD 3.1 and AD DAV minus OBT AV 1.4. The remaining 4 reported that they felt tired, their average ratio in the efficiency of memorizing being 80.6, with AD 14.9 and AD TAV minus OBT AV 6.8. On the whole then, those who felt worse had a greater degree of efficiency of memory. The chances are 99 to 1 that those who report that they feel tired will have a greater decrease of efficiency in memorizing than those who report that they feel medium. By the third method, we obtain a coefficient of correlation of 0.99 between the changes of feeling and the memory ability. The feeling of fatigue and the decrease of efficiency in the function exercise in mental multiplication of a 2-place number by a 2-place number. The decrease of ability is shown by the ratio of the average time taken per example in the last 10 minutes to that in the first 10 minutes. Of 12 individuals, 6 reported that they felt medium and had the average percentage of 76.3 with AD 15.3 and AD TAV minus OBT AV 6.3. The others, reporters having felt tired, had an average percentage of 97.3 with AD 35.0 and AD TAV minus OBT AV 14.6. There is a probability of 6 to 1 that those who feel medium will on the average show less decrease of efficiency in the function. By the third method, the coefficient of correlation is found to be 0.37 between the change in the feeling and that in the efficiency of the function of mental multiplication. End of section 4. Chapter 5. The influence of mental work on the efficiency of mental functions. Methods of measurement. A glance at the figures in the tables of Chapter 2 will show that the subject does not work with higher speed in the second than in the first test. The favorable influence with the continued exercise of a function exerts on its own efficiency and which does not entirely disappear within a few minutes is called the effect of practice. A comparison between the speed of performance at the beginning with that at the close of a course of work, shown in Table 4 on page 38, shows that the former is much higher than the latter. The unfavorable effect which continued exercise of a function produces in its own efficiency is called fatigue. That which it exerts on other functions is called transferred fatigue. The amount of practice gained during a certain work period is measured by the excessive ability after a certain length of rest immediately succeeding it over that at the beginning of the work period. It is of course impossible to measure the exact amount of practice gained, for too long a rest causes a considerable loss of practice, while too short a rest does not completely eliminate the effect of fatigue. The measure which I shall use for the practice gain is obtained by taking the percentile gain in efficiency of the function when tested under similar conditions of rest. The ideal method of investigating the fatigue is to test a subject who has approximately reached the limit of practice in the work used. Under ordinary circumstances, however, it is not easy to get such persons. In our investigations, the subject T.A. was apparently in a very high stage of practice in mental multiplication. See Experiment 1, page 2. With these materials, we measure fatigue by simply taking the difference between the efficiency at the beginning of the period and that at the end. The coefficients of fatigue are obtained by these tables by two different formulas according as different units of efficiency are used. The formula A is used when efficiency is measured by the time taken to do a given amount of work, and the formula B when it's measured by the amount of work done in a given time. A coefficient of fatigue equals T2 minus T1 multiplied by 100 over T1. B coefficient of fatigue equals A1 minus A2 multiplied by 100 divided by A2. T1 and A1 equals time required and amount done at the beginning of continuous work. T2 and A2 equals time required and amount done at the end of continuous work. In the case of transferred fatigue, T1 and A1 and T2 and A2 represent the efficiency before and after some hours of mental work. We must use, however, a method slightly more complex in dealing with figures, including the influence of practice. There are two different methods which were used by previous investigators. One is a method used for the first time by Professor Thorndike, and the other that used by Kraepelin and his pupils. The writer will summarize, according to her judgment, two articles which represent the two methods and try to decide for our investigation. The first is Mental Fatigue by E. L. Thorndike, published in the Journal of Educational Psychology, Volume 2, Number 2. 1. The function studied. The mental multiplication of a three-place number by a three-place number, neither having any zeros or ones amongst the digits. 2. The subjects. 16 students, sex not stated. 3. The method employed for the test. Each measures the time he takes for getting the answer of each example. He works continuously on one day and the next day for a half hour or 1 hour. 4. The method of calculating the amount of fatigue is measured by the percentage which the time taken to multiply certain numbers of examples at the end of one period is of that after certain hours of rest succeeding the work period. The second is Über Arbeit und Ruhe by Ernest H. Lindley, published in Kraepelin's Psychologische Arbeiten, Volume 3, page 482 to 534. 1. The aim of the investigation is to ascertain the factors determining the work curves, which are practice, fatigue, Gilwang, warming up, and initial and final spurts. 2. The subjects, 2 men and 1 woman. 3. The function studied, adding one-place numbers. 4. The method of measuring the efficiency of addition, by the number of single additions. 5. The method of the test. Each subject works for 1 hour continuously on the first day, for the two 30-minute periods, with 5-minute rest between on the second day for two 30-minute periods, with 15-minute rest between, on the third day for two 30-minute periods with 30 minutes rest between, on the fourth day for two 30-minute periods with 60 minutes rest between, on the fifth day. The same program is repeated for the next 5 days. On the 11th day, the subject has a complete rest. The tests are made on the next 10 days, following the same arrangement of hours as in the first 10 days. Another complete rest of a day follows here. For the next 5 days, the same program as was used for the first 5 days is employed, but is followed by a day with 1 hour of continuous work. We shall call, for the sake of convenience, the first 10 working days Group A, the second 10 Group B, and the last 5 Group C. 6. The methods of measuring each factor contained in the results of the tests described above. 1. Finding the best rest period. Take the length of rest which brings about the greatest success of the amount of work done in the second 30 minutes over the amount of work done in the first 30 minutes. 2. Finding the practice effect. Subtract the amount of work done in the first 30 minutes on the first day of each of the 3 groups from the amount of work done in the first 30 minutes on the last day of the same group. Divide the answer by the number of the days between the two extremes of each days. By getting the average of the 3 groups is obtained the amount of daily gain for each subject. 3. Finding the amount of Gyeowonang. It is defined by Lindley thus: Der Gyeowonang zeigt sich in der Schnelligkeit, mit der man sich von inneren Untersuchungen Studenten erfussen, unabhängig zu machen imstande ist. For making a rough estimation of it, get the excess of work done in the first 30 minutes of the working period of the second day of the work done in the same period on the first day of each group. 4. Measuring the rate of practice gain from 30 minutes work. The work after the best period of rest is held to contain a minimum amount of loss of practice effect, fatigue effect, and warming up effect. Suppose this to be true. The excess of the amount of work done after the best period of rest over the amount of work done before it may be attributed to the amount of gain due to the 30 minutes work preceding. The ratio between this excess and the amount of work done after the best period of work is taken to be the rate of 30 minutes practice gain. 5. Measuring the persistency of the practice gain. As the persistency of the practice gain relates to its loss in an exactly inverse ratio, the latter is taken to be a measure of the former. To find the loss of practice gain during X period of rest, we must calculate first the amount of work which would have been done after the rest, if there were no practice loss at all. This is done by multiplying the amount of work done before the rest by 1 plus the rate of 30 minutes practice. The difference between the reckoned amount and the actual amount of work done after the rest is attributed to the amount of loss of practice for, as during the best period of rest, the effects of fatigue and warming up are supposed to have disappeared almost entirely. What occurs during X minus best period is taken to be the loss of practice gain. 6. Measuring the effect of fatigue. During 5 minutes rest, according to Lindley, warming up effect is almost lost, while the effect of practice and that of fatigue remain undiminished. Suppose that we find the amount of work done in the 30 minutes containing the effect of practice, but not of fatigue resulting from the 30 minutes of work preceding. Then the difference between this and the actual amount of work done after the 5 minutes rest may be attributed to the amount of fatigue. The said amount of work containing practice effect only is obtained by multiplying the actual amount of work done before the 5 minutes rest by 1 plus the rate of the 30 minutes practice gain. 7. Measuring warming up effect. A comparison of the amount of work done in the 6th 5 minute, i.e. the last 5 minutes, of the first work period and the amount of work done in the 7th 5 minutes, i.e. the first 5 minutes of the second work period, shows a certain decrease in the latter after a rest of 5 minutes or more, and the amount is more than the average amount of loss of practice gain during the same length of rest period. Both methods are based on the supposition that the amount of gain through rest can be a measure of fatigue resulting from the work immediately before rest. The point of divergence of the two methods lies in the further presuppositions. Lindley presupposes that the best rest brings about the least loss of practice gain and the greatest recovery from fatigue, and naturally that if there were no fatigue at all after 30 minutes of work, the amount of work done the next 30 minutes, less the gain in warming up, should be the same as that done in the 30 minutes after the best rest. Therefore, the greater part of excess of this reckoned proportion is attributed to the amount of fatigue. But from a practical point of view, the validity of Lindley's presupposition depends on the amount of practice gain lost during the best rest. If it is a negligible quality, the problem is simply to find the difference between efficiency in the next 30 minutes and that immediately after the best rest. But if it is a considerable quantity, the efficiency after the best rest will vary according to its amount, provided that the fatigue effect remains the same. According to tables 3 and 5 in Lilly's article, pages 495 to 500, in the case of subject B, the amount of loss of practice gain in the second 30 minutes work period is 11 and the daily loss is 50. Therefore, 1/5 the whole amount of practice loss during a day is lost during the second 30 minutes. The loss of the first 30 minutes, according to this rate of loss, should be approximately 20, since the amount of B's fatigue is found to be 42 according to Lindley's method. The true amount of fatigue should be about 62 if the amount of recovery outweighing the negative influence of practice loss is counted. Therefore, Lindley's method is justified only when there is the least amount of practice loss. Thorndike's method disregards practice loss entirely. Its validity depends on the length of rest. If the length of rest is so much that it would cause a great amount of practice loss, or if it is so short as to leave a large amount of fatigue, the method is inadequate. With our present materials, we cannot use Lindley's method, for our investigation was not carried out with so many varieties of length of rest as Lindley's. On the other hand, we shall not always follow that of Thorndike exactly. He studied the amount of fatigue by taking the ratio of the time taken before rest to that after rest. But in our investigation, we shall, when practice is not negligible, use the ratio of difference between the efficiency before rest and that after rest to the latter. We shall, for the sake of convenience, call the method of comparing efficiency before and after the work period Formula 1, and that of comparing efficiency after the work period with that at the beginning of the next work period, i.e. after rest, Formula 2. Reducing accuracy and speed to 1 unit. Quantity and quality are two essential elements which we must consider in determining work done. Kraepelin and his collaborators, however, attached great importance to the former, disregarding the latter. Professor Thorndike attempted to do justice to both of these elements by adding some amount of time for each error. In our investigation, the question arises only in the case of mental multiplication. If errors are distributed evenly in the course of work, they may be due simply to chance, and we may disregard them in the study of fatigue. However, according to the results obtained by Experiment 1, the errors bear certain relations to practice and fatigue, as will be seen in later pages. So it is not justifiable to disregard them. For this reason, we add 10 seconds for each wrong digit in the answers of all multiplications. Fatigue in the special function exercise in all cases of individual TA. The materials are obtained from Table 1, 2, 3, and 4. 1. The amount of fatigue. In order to know which formula to use in getting the amount of fatigue, we have to determine the amount of practice involved in each observation. The results of the calculation run as follows. A table is displayed on the page, time taken in minutes and seconds, and errors made per example in the first 5 examples on each experimental day. Table 17 is displayed on the page, the sum of the time taken plus 10 seconds for each error for each 5 examples at the end of each continuous work period, expressing the efficiency before each rest. A similar record at the beginning of the succeeding work period, expressing the efficiency after the rest and the coefficient of fatigue. In the figures given above, 2 important facts are noted. 1. The gain in speed as a result of each test is greater in the beginning and becomes slower as it approaches the end. 2. Some practice gain is still observed in the tests of the last 4 days. However, the average daily practice gain being 30 seconds in these tests, the average practice gain per example in the course of 12 hours of mental multiplication is only 0.04 of a second. The gain per example is so small that in our study of fatigue curves it may be disregarded. The coefficients of fatigue are obtained by Formula 2 and given in Table 17. The figures given above indicate that mental multiplication of 4 practice numbers by 4 place numbers continued from 1.7 hours to 12 hours causes more or less decrease of efficiency in the function exercised. The amount of fatigue in the last 4 tests as determined by Formula 1 is given in Table 18. Table 18 is displayed on the page. Averaging the 4 tests, we find that 12 hours of mental multiplication results in a reduction of speed to less than 1/2 of the original speed. The average coefficient of fatigue thus obtained is 93.2. The average coefficient of fatigue measured by Formula 2 is 106.1. Therefore, the true coefficient of fatigue, that is increased in time required as a result of 11 hours of this work, would be near 99.6%, the average of the two. 2. The course of fatigue. The course of fatigue is represented by a curve made by the following method. A horizontal scale line for the number of examples is drawn. The height of the curve at any point represents the time taken for an example. The rise of the curve, therefore, means decrease of speed or increase of the time taken to do a given amount of work. Curves 1 to 5 represent the course of work according to Experiment 1, Part 1. The curves bring out 2 important points. First, the length of the curve increases in the latter tests. Since the subject ceased to work the very moment when she thought it desirable to do so, the increase of the working period means that the subject's ability to continue the work increased. This is either because the subject gained by practice a greater power to resist the impulses to stop work, or because the work became actually easier as a result of practice, or both. Second, the form of the curve varies according to the amount of practice. In general, the curve first falls and then rises. This shows that the end of practice is stronger than was that of fatigue at the beginning, and vice versa towards the end. In the earlier tests, the fall and rise of the curve are more marked than the latter tests. This signifies that both gain by practice and loss by fatigue become smaller as one's practice is greater. Similar points are observed in the course of work in each of the tests of the practice series of Experiment 2, Part 2, which are given below in curves 6 to 11. As was explained in Chapter 2, the tests on the last 4 days of Experiment 1 were performed when the subject was in a very late stage of practice, and the gain by practice in the course of work is of a negligible quality. Therefore, the results of these tests may be considered as representing the course of fatigue in a relatively pure form. Curve 12 shows 1. The 4 different curves representing the course of work in the 4 different tests, and 2. The curve representing the average of the 4. The divergencies of the separate curves from the average curve are such that the true average curve obtained from an infinite series of experiments will, on the average, not differ from the average curve shown in curve 12 at any point by more than 12%. The chances are 8 to 2 that it will not so differ in one direction. For the study of the fatigue curve in individual TA, the average curve will be used throughout. It shows the following important characteristics. 1. The curve does not fall at the beginning, as do the other curves already shown, but rises from the beginning. 2. It rises gradually up to the 34th example, fluctuating above and below the standard line. Then it takes on a different aspect, the curve being above the standard line, up to the 56th example. The rise of the curve is due to decrease of speed. It falls at the 56th example and continues to be below the line until example 61. It ends with another rise. Many explanations can be given for the shape of the curve. One explanation is to suppose that, at the point where the sudden rise of the curve begins, example 35, the subject yields to the feeling of fatigue, letting herself go for a while. During the relaxation, the subject is recovered from the effect of fatigue to some extent. As a result of this, efficiency again increases, and the increase of efficiency results in the fall of the curve. Examples 44 to 60. Another way of interpreting the form of the curve is to attribute it to the diurnal course of efficiency, i.e., to suppose that the subject accomplishes more at one time of the day than at another. According to the curve given above, the sudden rise occurs at 5 p.m. The fall of the curve occurs at 8 p.m. and lasts until 10 p.m. This falls in with the subject's habit. The subject is accustomed to spend the time between 5 p.m. and 8 p.m. in recreation, while the hours between 8 p.m. and 10 p.m. are reserved for intellectual work. The slope of the curve may be due to this habit of mind. The examination of curve 5 for February 22 shows that the sudden decrease of speed occurs at the 35th example, i.e. at 5 p.m., although the subject had worked for only 4 hours instead of 6. 3. Aside from the fluctuations noted above, The rise of the curve seems on the whole to be gradual. Since these fluctuations are explained by a fact other than the onset of fatigue, the onset of fatigue may be regarded as gradual. 5. The difference between the time taken for one example and that for another is greater in the second half than in the first half of the curve. This fact, together with the evidence of introspection of the subject, suggests that fatigue not only causes decrease of efficiency, but also loss of the subject's control over herself. For this reason, the subject tends to occasionally relax her original standard of effort. 3. Warming up effect. The results show little or no effect of warming up. If there were any such effect, it would show itself before being overcome by the fatigue effect, and would make itself manifest in the fall of the curve soon after the beginning. There may be a slight effect of this kind. If so, it is so small that the effect of fatigue outweighs it from the beginning. 4. Spurts or Antrieb. There is nothing in our curves which correspond with Anfang und Schlussantrieb, or initial and final spurt. The times taken for the first and second 4 examples at the beginning, as well as those taken for the first and second 4 examples from the end, are given below in minutes and seconds. A table is displayed on the page. The difference between the first and the second 4 examples at the beginning and that between the first and second 4 from the end are not regular in all our experiments. 5. Accuracy and fatigue. The average number of wrong digits per answer in each successive 10 examples in each test is as follows. A table is displayed on the page, order of each 10 examples. On the whole, accuracy decreases as the work progresses. Fatigue and the special function exercised in the case of the group of individuals, the materials being obtained from Table 8. The amount of fatigue. The effect of practice at each 2 hours of mental multiplication is measured by comparing the efficiency at the beginning of a 2-hour period and that immediately after rest succeeding it. The coefficients of practice thus obtained, see page 80 for the formula used, are given in Table 19. Table 19 is displayed on the page, coefficients of practice. The table shows that, in most cases, the amount of practice effect is greater in the first test than in the second test. In both cases, the cause of fatigue is involved with the increasing practice effect. Therefore, in measuring the amount of fatigue, Formula 2 must be used. The coefficients of fatigue in the 2-hour work period are given in Table 20. Table 20 is displayed on the page. A. The amount of fatigue measured by recovery during a 10-minute rest. The amount of fatigue measured by recovery through a 60-minute rest. C. The amount of fatigue measured by recovery through a 180-minute rest. The fact that the average coefficient of fatigue is about the same in both A and B, excluding C on account of its having too small a number of cases, suggests that the fatigue caused by 2 hours of mental work is very probably eliminated during a 10-minute rest, then that the loss of practice effect during the next 50 minutes is insignificant. Therefore, the greater part of the difference between efficiency immediately before and that immediately after the rest is attributed to the whole amount of fatigue caused during the work period. The average amount of decrease of efficiency caused by the 2 hours of continuous work is then, for this group, 24.2% of the efficiency after rest. Table 21 is displayed on the previous page, time taken per example in each 10 minutes by each, and by the average of all the individuals, also the average of all but the subject, JT. JT's records are eliminated in the second average on account of their irregularity. These averages are on the line of the star average. The course of fatigue. In experiment 4, all but 4 subjects took part more than twice. As the tests were made at different times and consequently in different stages of practice, they contained varying amounts of practice effect. For instance, the average time taken per example in each 30 minutes is, respectively, for subject MS, 131.1, 65.5, 56.1 and 55.7 in the first test, and 43.6, 35.6, 34.4 and 45.3 in the second test. Therefore, the average of the two cannot be taken as a typical curve of the individual as is generally done. This holds true with the average of the 2 tests of all individuals. We shall therefore present separately the results of the first and the second test as well as the average of the two in Table 21. The records of the first and second tests of 11 individuals out of 16 are given because they worked 2 full hours at one time. The following important points are to be observed in the figures given above. First, the absolute speed is greater in the second than in the first test by 25%. Second, the practice gain is much greater in the first test than in the second. The percentage ratio of the average time taken in the last 30 minutes is that the first 30 minutes is 79.9 in the former, while it is 96.4 in the latter case. Table 22 is displayed on the previous page. Average time taken to multiply per example in successive 30-minute periods. Third, there are 3 types of fatigue curves. The first type is represented by the curve which rises first and then suddenly falls in the beginning of the last fourth of the working period. To this type belong the curves MM, JT, and PFG. The second type falls and then rises in the second or third 30 minutes, showing that the effect of fatigue outweighs the effect of practice within 2 hours. To this type belong the curves CTR, SW, SN, and CHS. The last type falls gradually toward the end without showing clearly the point of maximum efficiency, for which the effect of fatigue outweighs the effect of practice. To this type belong most of the individual curves. Table 22 will show that these 3 types by the actual figures which show the average times taken to multiply per example in each successive 30 minutes. O'Hearn, in his study of 10 individual work curves of the 4 different psychomotor and mental functions, remarks that the maximum point is reached sooner in the more automatic functions than the purely mental functions, and that the average point of maximum ability is reached in memorizing the numbers, the most purely mental function, at the end of 60 minutes. Thorndike gives a detailed report of his investigation of fatigue curves, from which the present writer calculated the time when the maximum efficiency is reached in each individual curve and obtained the following results. A table is displayed on the page comparing the time when the maximum efficiency is reached and the number of individuals. 0 to 1 hours, 3. 1 to 2 hours, 1. 2 to 3 hours, 5. 3 to 4 hours, 3. 4 to 5 hours, 0. 5 to 6 hours, 1. 6 to 7 hours, 0. 7 to 8 hours, 0. 8 to 9 hours, 1. Our results therefore correspond with those obtained by Thorndike. There is a definite relation between the type of curve and efficiency in the function. The average time taken per example in the 2-hour working period of the first type is 123 seconds. In the case of 3 individuals, that of the 4 individuals belonging to the second type is 104.2 seconds. That of 9 individuals belonging to the third type is 48 seconds. Those who do not show the points of maximum efficiency are the best performers of the group. The types of the curves are, of course, determined by the relation of fatigue to practice effect. The greater the ratio, the earlier the point of maximum efficiency occurs, and the more marked the slopes of the curve. The relations depend either on change in the absolute amount of one of the 2 factors, the other remaining the same in amount, or on the change of both, each in different amount. From this fact, an important question arises, namely which of the 2, practice or fatigue, is the determining factor of the relation in our curves. In studying this relation, we have chosen the records of 8 individuals taken under relatively uniform conditions. Table 23 is displayed on the page, coefficients of fatigue and of practice of each individual, and the average coefficient of fatigue and of practice for each type, using the average of the first and second trials of each individual. According to the average coefficients of fatigue and those of practice in the 3 types, the curves of the first and second type contain a greater amount of fatigue than do the curves of the third type. While the practice effect remains the same in both cases, the difference in the form of the curves then is due to a difference of absolute amount of fatigue effect. Since it is found that individuals of the third type are much more competent in their work than those belonging to the first and the second, it is probable that the most competent workers are affected least by fatigue. Warming up effect. As a result of the study of the work curves after rest, it is found that a curve falls after a rest of 60 minutes, while it keeps practically the same level after a rest of 10 minutes. Table 24 gives the time taken for the first, second, and third 4 examples after both periods of rest. Table 24 is displayed on the page, time taken in doing the first, second, and third 4 examples after different lengths of rest. The difference between the form of the curve after the short period of rest and that for the work after the longer period of rest cannot be explained without supposing that a warming up process acts in the course of work and disappears soon after the cessation of work. This warming up process is more completely neutralized during the 60-minute rest than during the 10-minute rest, and therefore the efficiency immediately after the longer rest is less than after the shorter rest. Spurts. In our experiments, the subjects did not know when the end of the work period was coming. Hence, it is not possible to study the effect of final spurts from our records. For the study of initial spurts, the usual comparisons were made between the time taken for the first example and that for the second, between the first 4 and the second 4 examples, and also between the first and the second 8 examples. The writer did not find any uniform superiority of the first over the second interval. Accuracy and fatigue. According to the results of Experiment 4, accuracy in work does not seem to be influenced either by fatigue or practice. For 11 individuals who underwent 2 tests, the average number of incorrect digits per answer in each successive 30 minutes is 0.77, 0.72, 0.73, and 0.72 respectively in the first test, and 0.78, 0.80, 0.67, and 0.62 in the second. That the absolute number of mistakes is not less in the second trial than in the first suggests that practice has little to do with the number of errors. That fatigue did not influence the accuracy of the work is shown by the fact that in both trials the number of errors decreased in the course of work. Supplementary data. An experiment was made on the subjects TA and EBG for the investigation of fatigue in the function exercised in reading. TA read Dickens' Bleak House 3 hours a day and repeat the process for 5 days in succession. In this reading, the time of beginning every other page and the time spent in reading each 2 pages was computed. The results of this test are given in Table 25. According to the figures given above, the average time taken for reading each 10 pages on 5 days is, in minutes and seconds, respectively 27.07, 26.44, 25.51, 26.27, 26.56, and 27.43. The time decreases gradually to about the 40th page, the time increasing from then on to the end. It seems more reasonable to attribute the cause of the increase of speed in the beginning of the reading to the warming up effect than to the effect of practice, for its effect has no influence on the speed of the performance of the next day. Table 25 displayed on the page, the time spent in reading each section of 2 pages and for each section of 10 pages in both tests. EBG read Our Mutual Friend. The time for reading was recorded in the same manner as before, except that the record was made by the experimenter, not by the subject herself. The results are given in Table 26. Table 26 is displayed on the page, time spent in reading each 2 pages and for each 10 pages. According to the figures given above, EBG seems to have no warming up effect. Another experiment was performed on the subject TA for the purpose of investigating the effect of fatigue on the mental function exercised in filling blanks in sentences where certain words had to be supplied to make sense. This method was used for the first time by Ebbinghaus, who called it combinations method. Professor Whipple says concerning this, the author of the method says in substance, mental ability demands not merely retentive capacity, readiness of recall, or facile association of specific past experiences. It demands all this and something more complex, and, as it were, creative, namely, the ability to combine into a coherent and significant whole, mutually independent and even seemingly a combinative activity. To measure intelligence, therefore, we must employ a test that demands ability to combine fragments or isolated sections into a meaningful whole. Such a test may be afforded by mutilated prose, i.e., by eliding letters, syllables, words, or even phrases from a prose passage and requiring the examinee to restore the passage, if not to its exact original form, at least to a satisfactory equivalent of it. Of the difficulty of deciding the number of qualities of eliding words, the same author says, "The completion method is peculiarly difficult to class psychologically, for the simple reason that the nature of the mental process that depends almost entirely upon the number and kind of illusions that are made in the test. To take extreme cases, if the illusions are numerous and sweeping, it may become really a linguistic puzzle of a very different variety, and it then belongs rather to the group of tests of active or creative imagination of the literary type. If, on the other hand, the illusions are but few and simple, it may degenerate into a simple test of controlled association of any desired degree of ease." A careful attempt to eliminate the source of error was made in the preparation of the materials for the test. About 55 words were elided on each page of the 1910 edition of Thorndike's Educational Psychology in the manner shown below. The knowledge of human blank, which psychology blank to students of educational blank and blank may roughly blank into blank. A body of knowledge about instincts, habits, memory, attention, interest, reasoning, etc. Find blank in the ordinary blank books. Detailed blank of thoughts, feelings and conduct of certain blank at different ages are available in blank of child blank. The difficulty of the work differs with different individuals. Such materials as quoted above do not seem to be too difficult or too easy to serve our purpose. The test was begun at about noon and lasted to 9 p.m., with intermissions of a few seconds now and then spent in recording the body temperature and pulse rate, and with a 50-minute rest for supper. The subject recorded the time of beginning each page, and the time spent on each page was computed. The results are given in Table 27. Table 27 is displayed on the page. Time spent for each page and for each 5 pages in completing passages, together with the temperature and the pulse rate at irregular intervals. The figures given in Table 27 form another typical work curve. The speed increases in the beginning for about 2 hours. After that, it decreases gradually until the end. The rest for supper restores the lost energy to some extent, the time taken for the 5 pages after the first rest being 92.7% of that spent on those before the rest. The fatigue effect appears again in the second hour after rest. Transferred fatigue. 1. The effect of fatigue from continuous exercise of the function of mental multiplication transferred to other functions. According to the results of Experiment 1, mental multiplication lasting for certain hours without rest brings about such changes in efficiency in memorizing German words as are shown in Table 28. Table 28 is displayed on the page. Number of hours of mental multiplication, number of examples, time taken to memorize 40 German words, 10 being memorized at one time, both immediately before and after the mental multiplication, and a coefficient of fatigue. The minus sign in the coefficient column means an increase in efficiency as a result of continuous work. Table 28 shows that an average of 9.4 hours of mental multiplication causes a 21.4% increase in the time taken to memorize. The time of memorizing does not, however, increase in any exact proportion to the increase of the number of hours of mental multiplication. 11 individuals, Experiment 4, memorized nonsense syllables before and after 2 hours of mental multiplication. The effect of fatigue caused by continuous mental multiplication on the function of memory in each individual is given in Table 29. Table 29 shows that, with all but 5 individuals, the number of nonsense syllables remembered decreases during the 2 hours of mental multiplication. For all the subjects, the average decrease was 13.5%. Table 29 is displayed on the page. Number of nonsense syllables remembered before and after 2 hours of mental multiplication and coefficients of fatigue. 11 individuals underwent the association test before and after the 2 hours of mental multiplication. The effect of fatigue caused by the mental multiplication on the speed in associating the autonyms with given words is, for each individual, as follows. Table 30 is displayed on the page. Time of associating autonyms before and after 2 hours of mental multiplication and coefficients of fatigue. The foregoing table shows that 5 subjects out of 11 lose speed doing the mental multiplication, while the rest give opposite results. The individual differences are too great to draw any general conclusion from the figures given above. 9 individuals underwent the addition test before and after 2 hours of mental multiplication. The effect of fatigue caused by the work on efficiency in addition is given in Table 31. Table 31 is displayed on the page. Time taken for addition as described in Experiment 4 before and after mental work, and coefficients of fatigue. Here too, the effect of 2 hours of mental multiplication is subject to great individual differences. 2. The effect of fatigue caused by general mental work transferred to special mental functions. The materials for discussion are obtained from Experiment 2. 1 year elapsed between Experiments 1 and 2. The practice effect in Experiment 1 might still be at work in the test of mental multiplication in Experiment 2. The results show that practice has influence only on the first 8 mornings. In order to know clearly the effect of practice on the results of the memory test of Experiment 2, we must note the facts of a short preliminary test. During April 1909, about 10 months before the beginning of Experiment 2, the same subject made a series of practice tests of the function exercised in memorizing German words. Each day the subject memorized 5 lists of 10 German words each, and noted the time when she began to memorize each list, and the time when she finished writing them down in their original order. The same process was repeated 5 times at each test. The average time taken for memorizing a list on each day of the experiment is shown in Table 32. Table 32 is displayed on the page. The figures of Table 32 give a typical curve. The gain by practice is greatest at the beginning and becomes smaller as it approaches towards the end. After this preliminary experiment, the memory test of Experiment 2 was made. We find in this test the average daily gain to be about 0.18 seconds, and the gain observed in the morning test only 0.09 seconds. Therefore, in dealing with the observations made in Experiment 2, practice effect can be neglected without causing any grave error. The fatigue caused by general mental work during the day is measured by a direct comparison of the efficiency in the morning with that of the evening. If the results of the comparison show that fatigue through the day increases in proportion to the increase in the amount of mental work, we are justified in supposing that the fatigue is caused directly by general mental work during the day. The relations of these two factors are given in Tables 33 and 34. According to Tables 33 and 34, the transferred fatigue increases with the number of hours of mental work for both functions tested, at least from 3 hours on. Relations of fatigue in different mental functions caused by the same cause. In the foregoing section, it was found that fatigue in one function is, in part, transferred to some other mental function. The question rises here whether the transfer is equal for all functions. We can answer this question by calculating the coefficient of correlation between the fatigues of two functions. The correlations obtained between fatigue in the special function exercise and its transferred fatigue, and also between the transferred fatigue in one function and that in another caused by the same work. All the correlations which will be mentioned in this section were obtained by the Pearson method. In the case of fatigue from mental multiplication transferred to the function of memorizing, the correlation is minus 0.19 in the subject TA, according to the results of Experiment 1. The correlation is 0.21 in the group of 10 individuals, according to Experiment 4. In the case of fatigue from mental multiplication transferred to the function of association, there is no correlation, 0.003, according to the results of Experiment 4. Table 33 is displayed on the previous page. 10 different kinds of days according to different amounts of mental work done. 0 to 1, meaning a day of 0 to 1 hour of work. 1 to 2, a day of 1 to 2 hours, etc. Time taken to memorize per word in the morning and in the evening, and coefficients of fatigue, i.e. the percentage which the difference between the times taken in two cases is of the former. Table 34 is displayed on the page. This table is made on the same plans as Table 33, but with the time taken to do mental multiplication of 3 place numbers by 3 place numbers in place of the time of memorizing. In the case of fatigue transferred to the function exercised in adding, the correlation is positive 0.1, 0.088, according to the results of Experiment 4. For correlations between the transferred fatigue in one function and that in some other function caused by the same work, we have the following. In the case of the subject TA, according to Experiment 2, there is a correlation of 0.13 between the diminution in ability to memorize and that inability to do mental multiplication. In the group of individuals, according to Experiment 4, there is a correlation of 0.77 between the fatigue in association and the fatigue in addition. End of section 5. Chapter 6. Conclusions. 1. Mental fatigue and physiological processes. In the case of the individual TA, the morning to evening decrease in pulse rate was on days of less than 3 hours of mental work, 1.5%. On days of 3 to 6 hours of mental work, it was 3.9%, and on days of more than 6 hours of mental work, 7.3%. This decrease in pulse rate is correlated to decrease of efficiency in memory by a coefficient of 0.18, and to decrease of efficiency in mental multiplication by a coefficient of 0.17. In the group of individuals performing mental multiplication for 2 hours, there was a decrease in pulse rate of 13.3%, which decrease is correlated to loss of efficiency in memory, multiplication, addition, and association by the coefficients 0.73, 0.41, 0.24, and negative 0.14 respectively. We may therefore conclude that there is a decrease of pulse rate as a result of continuous mental work, which decrease is positively, though slightly, related to decreases in efficiency of the various mental functions tested. We are unable to draw any conclusions from the results obtained from our observations on body temperature during mental work. 2. Fatigue and feelings of fatigue. In repeated measurements on the individual TA, the direction and degree of change in feeling from morning to evening depended somewhat on the hours of mental work during the day. For instance, the feeling changed more toward the worse with prolonged mental work and vice versa. These changes are slightly correlated to the changes in pulse rate and in efficiency in memory and in mental multiplication. These changes seem to have no direct relation on the duration of sleep during the previous night. In the case of the group of individuals, we find similar relations between the degree of the feeling or fatigue, the decrease in efficiency of mental multiplication, and decrease in pulse rate. From these facts, we conclude that the feeling of fatigue is somewhat, though far from perfectly, correlated with the state of mental inefficiency. 3. The amount of mental work and changes in mental efficiency. 1. Factors which influence the efficiency of mental functions. In the course of several experiments on each individual, we find the efficiency increases during continuous work, and that this increase affects efficiency during the next experiment. We almost invariably find this favorable effect, the effect of practice, in the results of the experiment, except in a few cases where the subject has already reached the limit of practice. But we do not observe any regular warming up effect. In the 4 12-hour fatigue curves taken after the subject had reached the limit of practice, there is no initial increase of efficiency, but the results of the 2-hour experiment tried on the group of individuals perhaps shows the existence of the factor in question. In the reading experiment, the one who was less used to English showed this effect, while the other who had read it much more showed none. It seemed then to be a fact that warming up is not present in functions in which the subject has reached the limit of practice. For this reason, the writer is inclined to conclude that the warming up effect is only a part of the effect of practice. In none of our fatigue curves are the spurts observable. The unfavorable effect which is observed in our results is, of course, attributable to fatigue. Besides these factors, it is probable that habits of diurnal changes have some influence on the efficiency in mental functions. 2. The effect of mental work on the efficiency of the special mental function. Difficult and disagreeable continued work brings about a decrease in the efficiency of the function exercised. In the case of individual TA, the time taken to do a certain number of examples is almost doubled during 12 hours of mental multiplication. In the case of the group of individuals, inexperienced subjects, The increase in the time taken to do a certain amount of work is 24% during 2 hours of mental multiplication. 3. Transferred mental fatigue. Continuous exercise of a mental function not only causes a decrease in the efficiency of the function tested, but may have an unfavorable influence on other functions. For instance, in the case of individual TA, 9.4 hours of mental multiplication increases the time taken to memorize words by 21.4%. After 2 hours of mental multiplication, the group of individuals showed 13.5% decrease in ability to memorize nonsense syllables. But there was hardly any change in the functions of addition and association. General mental work decreases the efficiency of special mental functions. Fatigue and its transferred fatigue are, as a rule, correlated, though the correlation is very low. There is also a very slight but positive correlation between two transferred fatigues caused by the same mental work. On the whole, then, we are led to conclude that fatigue is a special mental function, as well as in general is slightly transferable to other functions, and the greater the fatigue, the greater the transferred fatigue. 4. Individual differences. We find great individual differences in the susceptibility to fatigue. As a rule, the more competent people are less affected by fatigue. End of section 6, and the end of Mental Fatigue by Tsuru Arai. Recorded by Leon Harvey for LibriVox.org.